professor in computer science at Uppsala University. He works in the intersection of design and implementation of programming languages, and most of what he does somehow ultimately comes down to memory management. Today's talk, the title of today's talk is How Should We Evaluate Garbage Collectors? So the floor is yours.
Thank you. All right, so let's do that. And let's do that. And let's do this. So let's see. Excellent. Right. Yes. How should we evaluate garbage collectors? So I originally had a somewhat more ambitious talk plan, but I couldn't really fit all of this into the 1 hour slot. So I scaled down my ambitions ever so slightly. Right. So this snake oil picture is not a dig at anyone or anything in particular. I tend to add a snake oil picture before any benchmarking result I present these days, mostly because, well, yeah, it's very easy, as we all know, I think, in this room, to get things wrong, even though you didn't intend to get it wrong, right? So to the extent you should believe benchmark results, well, you know, the devil is in the details, right? So, yes, this talk is, starting out well. I'll try and put that back. Right, so the gist of this talk is about convincing you people in this room and people listening that, I mean, when we evaluate garbage collectors, we want to really explore the entire deployment space, right? We want to see both memory use of high and low and go all the way up to sort of all of the memory that the systems are using, and we want to look at the CPU dimension in full as well. So that's sort of the thing that we want to look at. And my claim in this talk is essentially that what we are doing currently is we are looking only at one corner of this space. So we're constraining our evaluations to one particular corner of the space that we should be looking at. And the problem with this is that what we find when we look at that corner looks very little like what we find in the other part of the spectrum, right? So we're studying this gnome corner, right? And this gnome looks very little like the beast that we might find on the other end, right? So that's sort of the point I'm going to try to make to you. Okay. Great. So yeah, I'm going to be focusing on Java GC because that's essentially the thing that I know. And so let's start by looking at how do we evaluate Java GC today, right? And this is based on a survey of the last couple of years of GC papers in this space, so 34 papers in total. Okay, so how do we evaluate Java GC today? Well, as should come as a surprise to no one, probably, the Java evaluation space is dominated by the da capo benchmarks, right? So out of the 34 papers we looked at, 28 used da capo to evaluate GC performance, right? So da capo is dominating this space, and that's a good success and a testament to the quality and the ease of use of the da capo benchmarks that Steve and people around him have been developing, right? And the community is sort of quick to adapt to the new releases, at least the last release, the 23 release, is now dominating. I mean, it's actually dominating almost before it was officially released because you could already pull it off of GitHub and use it, right? And so we were seeing some uses of the original 2006 release going up to about 2021, and then that tapered off. We were seeing from the 2009 release, but now really the latest release is dominating. So people are following the development of this benchmark suite and are running the latest and greatest. So that's great. Okay, good, right? So the da capo benchmark suite comes with a couple of workload sizes, right? So there are the small workload sizes, the default ones, and the large ones. And well, there are some like very large ones for some specific benchmarks. There used to be a huge workload size that's, I think, now discontinued for the latest release. But what do people use? Well, people predominantly use the default workload sizes, right? So, like, that's the one that's dominating this space, right? So sometimes we see, for example, someone use small because they want to run stuff in a simulator, and that's good for possibly good for making the simulator run faster. Right. So in the Java space, when you want to understand the performance of garbage collection, then the concept of a heap size is super important, right? Because when you start your Java process, you need to tell it how much RAM can we use for on-heap memory, right? And that controls things like the frequency of garbage collection, right? So back in the day when we had mostly throughput collectors, you might give the Java process some kind of maximum heap size, and it would sort of use all of that heap space until it hit the limit, and then it would stop the world, do some GC, and then continue going again. And today we have more concurrent collectors, so we're using slightly more complicated heuristics where the goal may be to sort of keep the GC performance on par with the allocation pressure from or the allocation rate of the program, right? So obviously when we evaluate GC, picking a good heap size is super important, right? Because that will really control the GC performance of the benchmark, right? So what do people do? Right, so the predominant method for picking a heap size is this thing called the minimum heap method. Right, so it is essentially finding the smallest possible heap that you can use to run the program reliably without crashing, and then use that as your starting point for an exploration. So you might start at the absolute minimum heap and see, okay, when we're really starving the system, how does it perform? And then we give it maybe 2x that heap or 3x that heap, and so on and so forth. That's the predominant method. There are a bunch of other methods. Fixed heap size is typically, I mean, it's just finding a heap size and sticking to that. Could be because we've determined that the benchmark has its peak performance, or displays some interesting characteristics at that point. The concept of a stall-free heap, now we're going away from the minimum heap size, right? So to a more, let's say, concurrency-oriented way of thinking, right? So with a stall-free heap, let's pick, it's basically the minimum heap size, but changed for a concurrent world, right? So what's the smallest possible heap with which we can reliably run this program without the GC getting on the critical path of performance, right? What's the smallest possible heap that allows the GC to keep up with the pace of the allocation of the program? Right. Right. So yes, so minimum heap sizing, that's dominating the space. And what are the minimum heaps that people use to explore? Well, they look a bit like this, right? So the absolute dominating maximum heap size factor is 6x, right? So that means if you have a program with a minimum heap of 100 megabytes, you will explore that up to 600 megabytes of RAM. That's what you're going to give to the JVM when it starts up, right? So in summary, like, the capo is dominating this space. It's the latest release that are dominating the latest papers. Most people use the default workload size, and they use the minimum heap method for measuring or for deciding what's a good heap, and they scale this up to a maximum factor of 6x. All right, so that's the software side. Now let's look at the hardware side. So what are the machines that researchers use in these 34 publications to evaluate GC, right? So they're using fairly modern hardware. You can't see a time axis now on this, but as you would expect, it's sort of becoming more and more resourceful as time goes on, right? So we're seeing sort of 16, 32, 64 core machines. And in terms of memory, if you remove phones and sort of very particular deployments, you have sort of a minimum of 1 gigabyte of memory per core. But as you can see, frequently it goes above that that ratio, right? So smartphones have smaller amounts of memory, so we're seeing, let's say, half a gigabyte per core, or 0.75, something like that. So those are the machines that we are using to run these benchmarks, right? And if we look at cloud machines, so looking at AWS, Azure, GCP, OCI, we see cloud instances that you can sort of buy off the shelf with these configurations, right? So you have a bunch of different configurations of different sizes. They correspond fairly well to the machines that researchers are using, and the general purpose here is at 1 gigabyte per core, roughly, and then you can go above that. The absolute smallest one you can get some container-based configurations which are available with up to 4 cores, right? And then you can get below the 1 gigabyte per core line, typically. All right, so now we know the machines that we're using. So let's look at the scalability of the capo's default workload sizes in terms of CPU. Right? So this is an experiment. Now we gave these benchmarks 48x the minimum heap that they required, and we ran them on a 36-core machine and sort of looked at how do they scale, and this is the result. So most of these benchmarks do not scale, and that's precisely what they're intended to do if you follow the documentation. Then some of the scaling benchmarks, they seem to taper off at 4, 5, 6 cores, and if you go all the way up to 36 cores, then it's Sunflow and Zebra Crossing, or however you would pronounce that, that sort of allows you to explore all the way up to the limits of the machine. So it's 34 cores is where these peak out in this experiment, right? So that's CPU scaling. Let's look at memory now. All right, so the Da Capo default workload size has a geometric mean of 63 megabytes, right? So this is not per core, now this is the entire program, right? So it sort of has this distribution from Aurora, which uses 5 megabytes of heap, all the way up to H2 that uses 681 megabytes of minimum heap, right? And of course, what the minimum heap is will vary a little bit with what is the deployment configuration you're using, but these are the numbers that Da Capo itself reports, and I'm sure Steve will correct me if I'm wrong. Right. So if we map this back to the machines, right? Then if we take this minimum heap size method, and we start with the minimum heap sizes that we get from the benchmarks, and we try and explore it up to 6x, right? And we sort of map this back to the machines that we have and see how much of the machines we are using. Well, then the picture looks a little bit like this, right? So 75% of all of the configurations that we are testing, they use less than 1% of the available memory on the machine. So we're not using a lot of the available memory, as you can see, right? And if we change this to run the sort of the small container-based systems instead, with that typically has fewer amounts of cores, then well, we get to 75% of the configurations use less than 20% of the machine. So what does that mean? Well, I mean, you can interpret this in different ways, but our interpretation is that there's really a mismatch here between reality and how we evaluate GC, right? So if we, again, look at every red dot here on this graph is one actual configuration used in these 34 papers, right? And so that means that someone was using an 8-core machine with some amount of memory, for example, right? And so we have a thick line at 1 gigabyte per core here, and we're sort of plotting how much of the memory that's available that we actually use, right? So you can see most of these configurations fall well below this 1 gigabyte of memory per core ratio. And if we look at where the machines are, well, they're all up here, right? So they are above this line. So this is what I mean when I say there is a mismatch, right? We're evaluating things at sort of a space that's not really representative of the machines that we have on hands, right? So in summary, we're constraining our GC evaluation to just a small corner of the deployment space. And more speculatively, perhaps, you could make the argument that most GC evaluations use configurations which are unlikely to be used in real deployments, right? Because if you have a 64-core machine, you probably have 64 gigabytes of RAM or more, and we are constraining the programs to run at a small fraction of this available memory, right? If we gave it a little bit more, then maybe some of these effects of memory would taper off, right? So why are we doing this? Do we really think that the results that we are getting in this gnome corner there is sort of representative for what we get in the more beastly direction, right? So let's explore this a little further. So we're now going to be looking at a bunch of heat maps, right? And so these heat maps is an exploration of the da capo default workloads, right? So on the x-axis, you have the number of worker threads that we give to the program. So 1, 2, 4, 8, and 16. And on the y-axis, you have the amount of memory that we give to the programs. In this green rectangle, you see this is the space that would be explored if you use the minimum heap size method and you scaled up to 6x, right? The black rectangles, that's the 1 gigabyte per core configuration, right? If it's white space down there, you can see that's out of memory, right? So we're seeing, let's see if I can get a cursor in here. No, apparently not. But yes, you can see the space there, right? So this particular benchmark could not be run with a 37 megabyte heap or smaller, right? Yes, so what are we seeing in these cells? So in this, we're currently looking at throughput. We're going to be looking at more of this for more benchmarks. I'm just trying to tell you the notation right now, right? So 1.0, that's the highest possible throughput, right? So everything else is a factor slowdown, right? So 3.0 means this is a 3.0x slowdown of the maximum throughput that we could get. Right, so we're now going to look at 10 of the da capo benchmarks, the ones that report that they are trying to scale to to use the resources available on the machine, right? So throughput numbers, right? So what do we see? Well, we see first thing that you can notice that there is very little overlap between this green rectangle and this 1 gigabyte per core rectangle, right? So the black outlines and the green outlines, they rarely overlap, right? So H2, for example, is a good exception, right? So there they almost completely overlap, right? Because H2 has this 681 megabyte minimum heap size. If you go down to smaller worker thread counts, right? So we're sort of running the benchmark on a smaller number of cores, if you will, then we might see some overlap, but mostly the green space and the black space isn't really overlapping at all. And if you look at the bottom rows, right, you may see that giving the benchmark a little bit more memory seems to have some effect, but as soon as you go sort of a little bit higher up, then it's all down to how much CPU we throw on this, right? And so currently the da capo workloads, in the programs we're looking at now, they're defaulting to use as many worker threads as you have cores on your machine. So you would be looking at the 16 column, right? Okay, so right. So this is some way of looking at like if we were to run these programs with the amount of heap that's available on the machine, what's the effect of that? What would we see? So the effect is not so pronounced when it comes to the throughput results. Let's see if it's different for CPU utilization. All right. So now exactly the same kind of heat maps again, but now in each cell, we're looking at the amount of cores that were used on average throughout the entire execution. So 10.9 means we're using almost 11 cores at full speed on average throughout the entire execution of this program, and 1.6 means we're using 1.6 cores on average throughout all of this, right? And the green stuff and the black stuff, it's all the same. The only thing that's changed now is what's the meaning of the numbers in the cells, right? And so now higher is more CPU, right? All right, so what does that look like? Okay, so it looks a bit like this, right? So yeah, the overlapping of the green and the black, that's of course going to be the same, right? That nothing has changed here. We can see that in terms of what programs really scale up to use most of the machines. So we have Sunflow and we have Zebra Crossing, right? That's the ones where you can, if you wanted to test if your GC and your mutator thread is fighting over CPU resources, well, those two benchmarks might be able to give you a good feeling for that. But most of the others on a 16-core machine would give ample resources over to the garbage collector to do some work, right? So you would not be testing that particular scenario, right? And of course, we might want to test both these cases at the same time, right? In different benchmarks. Right, so CPU utilization, right? And yes, so most programs give you ample CPU headroom, right? And then finally, let's look at GC cycles per second, right? So now the numbers represent how many times did we do a GC cycle per second when this program was running, right? And so the black rectangles, they still stick, but now we're coloring them red in the case where we're seeing less than one GC cycle happening per iteration of the benchmark. So, right, so yes, and so for example, in this particular case, we see 230 GC cycles per second at the very bottom right corner there of the green rectangle, but just the one GC cycle per second for all of the red rectangles, for example. Right, so this is what we see, right? So notably the bottom rows here see very high frequency GC, right? So we're seeing sometimes, especially if we're looking at the 16 worker thread configurations, right? Where there are 16 threads that can now allocate data, right? That's of course going to exhaust the amount of memory that we have given to these programs faster, and so that will, increase the GC frequency, right? So we're seeing numbers in the hundreds for the very smallest possible configurations at the highest possible number of worker threads, right? And so this would not be possible if the benchmarks were using more memory, right? If they had a larger live set, that we would see a different cost profile, and you can see that if you look at H2, for example, there, even at the smallest possible configuration or memory configuration with the highest number of workers, you see 28 GC cycles per second. So that's like an order of magnitude less than many of the others, right? And that's because there is a lot of work for the GC to do in a cycle, because it has a larger live set, right? There's more memory to traverse, to mark, whatever is the algorithm, right? Oh, I should say, I forgot to point that out. These are all numbers now obtained with the G1 default garbage collector of OpenJDK 25, right? So this might look different, of course, if you run it with a different GC, but this is the default GC that I'm going to use as a baseline for essentially everything I'm telling you today. Right, so if you give these programs the 1 gigabyte per core that you have most likely, right, on most of these hardware configurations that we have seen, we're seeing fewer than one GC cycle per benchmark iteration. So that means if you're running 20 iterations of a benchmark, and maybe you're discarding the first 15 ones, and then you're looking at the average of the last 5 ones to get some kind of steady state, some of these iterations might not see any GC activity at all at this deployment, right? And so, in order to see GC activity, you need to, with these benchmarks, right, you need to press basically the amount of memory down in order to trigger more GC activity. But since we have pretty small live sets, there is not much memory used in these programs. We can see these very high numbers of GC cycles per second. That wouldn't really be possible if we had larger live sets, right? So, summarizing that, right? So again, we do not really explore this deployment space well, at least if we look at sort of what do people predominantly do with the best tools that we have at hand, right? We see this mismatch between CPU and memory, right? We're sort of running at the most CPU that we can use. So we're essentially treating CPU as a sort of free resource, but then we're constraining the memory that we're giving to these programs to a very small amount in order to sort of get some artificial GC pressure, if you will, out of these benchmarks, right? And the benchmarks live sets are very small, so that means you can have these sort of high sustained GC frequency, right? And we also see that there's ample CPU headroom in many of these, right? Yes, and as I already pointed out, right, if we size the heaps sort of according to what is the memory that exists on the machine, we'll see very frequently less than 1 GC cycle per iteration, right? Okay, great. So now we looked at the da capo default workloads, but da capo also has a large workload in the 2311 release, right? So let's do a little experiment, right? So let's start in the corner of the gnome and then sort of move a little bit towards the beast and see, like, do the results that we get when we are looking at the gnome hold up if we're running with the larger workloads, right? So do the results hold up if we increase the workloads, right? Okay, so a little bit of background, right? So I said we have the small, default, and large configurations for the benchmarks, right? So small, 5 to 157 megabytes of heap, and then default from 5 to 681, as we have seen before. And now we're going up to large, right? So large is 13 megabytes to 10 gigabytes, right? So 10 gigabytes, that's a substantial increase of a workload, but that's not all of them. So the geometric mean is 215 megabytes now, so at least we're seeing the next order of magnitude, if you will, right? So in this study, we're going to be focusing on those benchmarks that have a minimum heap size of at least 1 gigabyte, right? So we're going with Batik and BioJava, GraphKey, H2, H2O, and PMD. And then we took the Salon benchmark, which is just processing XML files, and we replaced some of the small XML files with larger files. So then we could grow the minimum heap size of Xalan to 1.8 gigabytes instead of 13 megabytes, which was the large workload standard, right? Okay, so we're now going to look at these 7 benchmarks and comparing the results obtained in default with the results obtained in large, right? But before we do that, let's look a little bit at what's the effect of the GC cost of, the CPU cost of a GC cycle in relation with the large and default workloads, right? So now we're looking at the heat map where we have the benchmarks on the y-axis and different heap factors on the y-axis, and we are in each cell figuring out what's the cost in GC CPU for the large workload per cycle, and dividing that by the cost of a cycle in default benchmarks, right? And so what we're seeing is a pretty big change, right? So there's somewhere between 2.2 and 121 times the higher cost in large, right? And of course, the freak result here is really the Salon benchmarks that we cooked up ourselves, not in order to get to this result, but just to increase the live set a little bit. And this is the result we got. But if you remove Salon, then you're seeing somewhere between 2 and 25x cost per GC cycle, right? So the cost profile is different, and it's also like a non-linear relationship really between the costs in default and the costs in large, because sometimes we see for H2, for example, like the more heap we give to the benchmark, the cheaper each GC cycle is, but that's not the case in H2O, for example. If we give it more heap, then each GC cycle is on average more costly, right? So we're seeing some interesting effects, right? So before we look at default versus large, let me just quickly plug some work done by Jonas, my PhD student. So in order to get this GC CPU measurements, he contributed to OpenJDK. That's now in production since OpenJDK 26. So if you give OpenJDK this xlog:CPU flag when you run it, then when the VM tears down, it's going to print this table that breaks down the costs of the various VM threads, right? So you will see exactly what was the cost of GC threads, and also in the serial collector where you're just reusing the main thread, that's going to be correctly accounted as well. So you can get a very nice breakdown of the GC CPU costs with some telemetry that is now in OpenJDK 26. Jonas has a nice blog post about this if you want to go look at it. I should point out the caveat that the barrier cost in mutators is not included, and this is, I mean, that's the big challenge, right, that we will eventually have to tackle, and this is super hard to do in an automated way, and it's super hard to do without getting all of these Heisenberg effects when you are trying to measure these things. But this is a step in the right direction, we think, and you can also, from within your Java program itself, query the results of like what's the GC CPU cost right now using this memory MXB. So you could use that, for example, to build an adaptive GC that looked at like what's the cost profile, what is the amount of CPU I'm willing to spend on GC, and adjust that using that number, for example. All right, good. So now let's look at some result comparisons, right? So let's start with JDK 11. So we're now going to compare this super cool LXR collector that was built in Steve's group with G1, right? Going from default to large, right? And so what we're looking at in each cell here is now basically the throughput. So you can think of that as the time it took to perform an iteration divided by the time it took to perform an iteration in G1. So G1 is always going to be at the bottom of all of these figures I'm going to show you, right? So that means that if we have a number that's smaller than 1, then LXR was faster. And if the number is larger than 1, then LXR was slower than G1. So let's look at Batik, for example, right? So in Batik, LXR was slightly slower than G1 in the default workloads, right? So 4% slower, 2% slower, and then, I mean, it's essentially on par, right? And then those effects are slightly increased when we go over to the large workload, right? So LXR was trailing a little bit, and then it's trailing a little bit more in the large workloads, right? If we instead look at BioJava, then LXR was 12% slower in the tightest possible heap, right? But then when we moved to large, all of that was essentially eradicated. It's almost on par, right, in the large workload. And interestingly, in the 2x and 6x and 12x heap factors, like LXR was faster than G1 on all of these configurations. But again, in large with the same heap factors, we are seeing almost an on-par result, right? So something is happening, both going from a regression being turned into on-par, and from an increase being turned into on-par, right? Let's look at H2O. Here is a super impressive result for the LXR collector, right? It's more than 30% faster. This is super cool, right? On the 1.3x heap factor. But again, going from default to large, right? We're seeing a 30% improvement turn into a 20% regression. So there is a huge difference there, right? And similar, very nice result on 2x, turn into a regression in large, and then on the 6x and 12x, then apparently G1 sort of seems to perform better if we give it more headroom, or alternatively, G1 requires more headroom than LXR, if you will. Then like regression is turned into an even bigger regression at the 6x and 12x heap sizes, right? Okay, so we can try and aggregate this in some way. So let's take the geometric mean of the default and large throughput numbers, right? So we see that on average, right, for the 1.3x heap size, LXR is a lot faster than G1. Right? Super nice result in the default benchmarks. But when we go to large, then that's turned into a regression, right? Same thing with the 2x heap size. It's an improvement that's turned into regression. Then it's an on-par result that's being turned into a regression, and then a regression that's being a little bit increased by going to the large workload size. So we're seeing like a 9% improvement going to an 8% regression by switching from default to large workloads, right? Okay, so let's move ahead to OpenJDK 25. So now let's look at ZGC versus G1 on OpenJDK 25. So default versus large again, right? So maybe the first thing to note is that a lot of these really tight heap factors we cannot give you a result for. That's because ZGC just the algorithm fundamentally needs more memory, so it ooms on many of these very tight heaps. But if you give it slightly more memory, it will run, right? So 3x, 6x, and 12x, we mostly have results for all of these configurations. So now, less than 1 means that GC was faster, and greater than 1 means G1 was faster. So in Batik, right, we have 0.05 result for ZGC, so 5% slower, 6% slower when we go to large, 2% slower on 6x in default, going to 1% slower on large, and then slight regression on 12x is turned to essentially an on-par result in large. Right, so there are changes here as well. Looking at H2O, right, there is a huge regression for ZGC on the 3x heap size, so it's 70% slower, right? But when we go to large, almost all of that is removed, right? So it turns into a 4% regression instead. And sort of similar for 6x, now given more memory, it still was running slower than G1, but in default versus large, we see a lot of that being changed or reversed, right? And on par, given enough memory in both default and large, right? So summarizing all of that, right? So we see we're going from regression to again regression, but a much substantially smaller regression, right? So we're going from a 32% regression to a 7% regression in total by going from default to large workloads. Right, moving on, let's look at the last comparison. Now this is parallel GC versus G1, again on OpenJDK 25, right? So in this case, less than 1 means that parallel is faster, right? And so, right, let me back that up. Right, so rather than going through and looking at all of the individual benchmarks, you can see if you look at them, like some go in one direction, others go in another direction, but on average, if you permit us to aggregate them using the geometric mean like that, well, it seems that there is really no difference when going from default to large on the 3x and 6x heap sizes. However, on the 12x, right, so we saw parallel was slightly faster on 12x, but then it's a lot faster on 12x with the large workloads. However, on the very tight heap, right, so we have a huge regression on parallel for these benchmarks, turned into still a very large regression on large, but substantially smaller, right, from 2.59 to 1.7, right? So all in all, it's 25% regression turning into a 12% regression, right? And you could ask, like, is this a valid way of counting? Well, it depends, right? I mean, I think implicitly in this way of looking at it, we are saying every configuration has equal weight, right? The 1.3x heap and the 12x heap, they are worth the same, right? You could argue something differently, but in this case, we're saying they are all equally valid configurations. Right, so in summary, we're seeing pretty large changes when we go from default to large, right? So it's a 20% difference in LXR, there's a 25% difference in ZGC, a 12% difference for parallel, right? We're seeing improvements turned into regressions and regressions turned into smaller regressions, and we're seeing some results holding up in parallel, but then when heaps are tight, there are very big changes in the results, right? And this is like more than what most papers demonstrate when we sort of make improvements to our GC algorithms, right? And this is, of course, because the cost profile for these larger live sets is fundamentally different, right? So we're not like flushing our T-labs a couple of hundred times per second, and we might not be scanning RAM sets or whatever it is we're doing, depending on the algorithm, right? So there are other factors now that start to dominate the cost profile of doing GC, right? And this is not just OpenJDK 25, right? This is also on OpenJDK 11. It's not just production GCs, because we also use the mature LXR version, right? So like this seems to hold up, right? So you might ask yourself, is this just a consequence of the capo then, right? So let's try and answer that question briefly, right? So now let's see if we can reproduce these results using SpecJBB 2015. Right, so SpecJBB 2015, this is a program that's simulating a web store essentially, right? So you have customers coming and buying goods from this web store. And what we are going to do now is we're going to take some constants in the SpecJBB 2015 benchmark, which is the number of items that in the store, customers, and the retained receipts. And we're going to scale that up and down because that will vary the live set of the program, right? The algorithm is still the same, the sort of the number of requests that are being made, the relation between saturation requests and probe requests is exactly the same, but the live set is different, right? And we use that to create a number of different workloads. And let's see if what we see in these results look similar to what we just saw in Da Capo, right? So, okay, so we have these 8 different workloads, A to H. Should point out F is sort of now the workload factor, the one we use to scale all of the number of items, customers, and retained receipts is 1. So this is essentially your vanilla SpecJBB 2015 configuration, right? So that's F. So we're scaling things down a little bit, going to the left, and we're scaling things up, going to the right, right? So we can look, for example, at the A and B configurations here. So now we're giving these programs 0.5 gigabytes of heap. So these are running now very constrained, right? Sort of similar to kind of a min heap situation, if you like, on a 28 core machine. And sort of the min heaps that we calculated here is 0.4 and 0.45 gigabytes. So we're running fairly close to that space, right? And now the workload factor for the A and B configurations is scaled down by 10 and then another 10 times to get from B to A, right? And that has some impact on the live set, as you can see, right? So what do we see? Well, when we go from A to B, right? So we're essentially touching the live set a little bit. It's a 33% increase of the live set, right? So we see throughput reduction for A1, that's the blue bar up there, of 20%, right? If we look at the D and E configurations, which are similar to F, right? We're giving it, again, 28 gigabytes of memory, right? So that's 1 gigabyte per core. And in the E workload, we've scaled down the number of items, customers, and retained receipts by 10, factor 10, and then we're doing it again to get from E to D, right? So we're seeing some substantial changes in live set here, right? So we're going from 0.27 live set in the D configuration and 0.4 gigabyte of live set in the E configuration to 2 gigabytes in F, right? So it's sort of, again, similar to going from default to large, if you will, in Da Capo. We're seeing some similar results here, right? So we're seeing a reduction in throughput from D to F of about 18% and from E to F, 22%. And if we bring latency into this picture, then the effects are even more pronounced, right? So going from A to B, that's a 50% reduction in latency operations per second, 40% for D to F, and 46% from E to F, right? So we're seeing sort of similar kinds of effects here, right? I should point out this H configuration is pretty unusual, right? So it's 768 gigabytes of memory for a 28 core machine. I mean, that's something that you can find in one of these cloud configurations, for example, if you will, right? And if you're running that, you can see some interesting results that, for example, the latency score of ZGC is really showing off there its algorithm. Right, okay, so let's look at GC cycles per second. All right, so again, in the very constrained heaps, we're seeing, just as we'd expect, a higher GC frequency, right? So it's not up in the hundreds yet. It's almost going there in the B configuration for the 0.5 gigabytes of RAM with the 0.45 minimum heap size, sort of 60, 70, somewhere there in that space. For the ones where we have about 1 gigabyte per core, we're seeing numbers of roughly around 1 GC cycle per second, right? For those configurations, right? And if we look at GC CPU, well, so it's pretty clear that when you scale up these factors that increase the live set, you're seeing sort of an additional cost in terms of what the GC needs to do, even at this small number of cycles per second, right? Compared to what we've seen for those other benchmarks, right? So the cost profile again is different, right? All right, yes. So let's summarize, right? So SPECjbb 2015, right? Experimenting with this benchmark seems to say that, well, this is certainly not an effect of the capo, right? This is something that is perhaps more fundamental to GC, right? So varying the live set will change the results significantly, right? Using more memory will change the results that we report in evaluations, right? And it also suggests that these small workloads, right, it shouldn't be used as proxies for what we'd see in the larger workloads at all, right? So sort of what we are doing isn't necessarily representative of what our users, the ones we are building these GCs for in the end, right, are likely to see, right? Okay, so let's get a little bit constructive, right? So where do we go from here? Well, so I think a first thing we should do is we should not use the minimum heap size methodology. We should instead use something that I would like to call representative heap. So we start with deployment-based heap sizing instead of workload-based heap sizing. So we're looking at what are the systems for which we are building these GCs out there, and then we start from there, right? So for a general purpose system where we're expecting to have about 1 gigabyte per core, well, that's a good starting point for what is the amount of memory that we should give to the programs, right? And then we can sweep up and down in fixed increments instead. So maybe 250 megabytes per core or whatever is reasonable, right? So that gives us sort of deployment sensitivity over workload sensitivity. And that's nice because sometimes when you see like, okay, so we're running this now with a 6x min heap, what does that mean? Well, it means very, very different thing if your min heap is 13 megabytes or it's a 681 megabytes, right? If you have a GC that's using 2 megabyte per core T-labs on a 32 core machine, well, you're eating up 64 megabytes of RAM to those T-labs immediately, right? And so giving a program 78 megabytes of heap may seem like it's an ample overhead, but it really isn't. And I guess this is like because we're building GCs today for like a different class of machines than what we used to do some time ago. So if we now take these representative heaps and we start using them, what's the consequence? Well, the consequence is, of course, we need to use the benchmarks that I would argue that we need to do that anyway, but we need to change the benchmarks to fit the machines that we use to evaluate GC, right? So we want them to be more scalable in terms of CPU, and we also want to have these larger live sets. We need to use more of the memory that's actually on the machine, right? And with sort of working with what we have today, I think we need to change the way we run these existing benchmarks. So for example, if we aren't using more than a couple of cores of the machine, well, why don't we constrain the evaluation to just run on that machine? I mean, who would run something that scales to 6 cores on a 64 core machine? I think that is an unlikely deployment. It would be more interesting to run it, limiting it to 6 cores, right? And that might also push it down into the representative heap sizing, right? Because if we're running with just 6 cores or 0.5 vCPUs or something like that, then of course we should also give this program less memory as an effect of that, right? So that to some extent removes problems with varying the free resources that we give to GC, because we're removing some of the free CPU. And I would also say that we should favor running these large workloads that are already there, right? That Steve's group has already engineered for us instead of the default ones, or maybe run both to show what is the sensitivity to workload sizing, right? Because still the large workloads, they are not that large in relation to the machines that we are using. But I mean, in lieu of having benchmarks that capture all of that space, then at least if we can see something along the lines of what you'd expect to see when benchmarks scale up in terms of live sets, that would be interesting, right? And of course, we have no way of knowing that if we scale up to the full extent of the machine, then maybe these results that we saw going from default to large might flip again, right? We simply do not know, right? There's nothing that says that this needs to be sort of a monotonic change, right? And as a consequence of this, it also means that GC benchmarking will take a little bit more time, but I think this is a good time investment, because I think that means that the results that we are producing are more meaningful for the systems where these GCs are likely to be deployed, right? And a lot of this work can be done with just what we have today, right? So you could, for example, change some of the existing Da Capo benchmarks to have a larger workload. So this is an experiment changing Cassandra from 150 megabyte live sort of minimum heap to 1.5 gigabyte minimum heap, right? And 1.5 gigabyte is still pretty small for a Cassandra deployment, but it is different than, I mean, considerably larger than the 150 megabyte. And again, we can see latency effects immediately as a consequence of that. And they, as I said, they might flip again when we go up to, let's say, a 15 gigabyte minimum heap size. We simply do not know, right? And we do not present these evaluations in our papers, right? So here is an example of what such a sweep could look like, right? So now we're looking at SpecJBB, and we're varying the amount of cores that we give to SpecJBB and the amount of memory that we give to SpecJBB. And that means that, like, if we're looking at just a row with a 4 gigabyte heap, but going all the way up to 64 cores, well, that's 64 megabytes of memory per core, right? So that's a very constrained configuration, whereas if you go with a 256 megabytes of heap on a 4 core, well, that's 64 gigabytes per core, right? So a lot. And by just looking at sort of the gradients of these, we can get a good intuition, or at least I feel we can get a good intuition for how these algorithms behave, right? So it's pretty clear that parallel, which is the top left one, right, in terms of throughput, as soon as you give it enough memory, that's somewhere between 16 and 32 gigabytes, I think some of the gradient effects aren't coming through perfectly on the beamer. But after that, it sort of doesn't really matter how much memory you give it. It's just CPU. That's the thing that matters. If you look at ZGC, well, you really need to give it a lot more memory in order to get to the same kinds of throughput results that that parallel will give you already at 32, right? If you look at latency, right now, sort of we're seeing a completely different way that the gradients are scaling, right? So sort of if we looked at throughput in parallel, it was horizontal essentially, and now it's almost vertical, right? So now the more memory we give it, that memory seems to be very important for getting a good latency result for parallel, and that's even more emphasized if we look at the strictest SLA, which is 10 milliseconds for SpecJBB, right? And it's pretty clear sort of where the ZGC algorithm tries to favor, right? And you can see the G1, which is sort of trying to deliver the sort of a little bit of both, right? It's trying to get good throughput and not too bad latency. It seems to be working out pretty well according to just this one SpecJBB result. So in conclusion, I think that data shows that we are constraining GC evaluation to just like a small corner of the space that we, I think, should be exploring, right? And many of the GC effects that we have, they vanish if we use representative heap sizing. So we scale programs up to the memory that we essentially already paid for in most of these cases, right? And I think we should adopt new workload sizes and benchmarks that permit exploring this entire deployment space. And I think, I mean, a really good way of doing that, right, is by leveraging this super nice deployment platform that exists thanks to Steve and the Da Capo benchmarks, right? But On the other hand, the large workloads have been around for a very long time, and it seems that they aren't being widely used and they're not widely reported in papers, right? So it's not just about changing the workloads, it's also about changing the mindset of our community to use these large workloads. And this is, I had on the previous slide, this means GC evaluation will take more time, right? Doing GC evaluation on the large workloads, that will run a lot slower than doing it on the default workloads. And that's probably sort of the effect that we are seeing. And maybe that means that we should just replace the meaning of small and large and default to something that sort of increases these numbers a little bit, gives you a slightly larger heap size. Right, oops. Final bullet on the final slide, so you don't need to stress tomorrow. Right, yes. And I think we should also switch from workload-based to deployment-based heap sizing, as I have said. Right, and that if we do that, that immediately stresses the limitations of the benchmarks that we have, because we're not running with these artificially small heaps. So that's it. Thank you.
Thank you for the nice talk. The time is limited, but I'd like to accept a couple of questions.
Thanks. I guess you're expecting a question from me.
I was, yes.
Yeah.
Or possibly a comment.
Yeah. So first of all, I think there's a little bit of a conflation of concerns here between benchmarks and methodology, and we need to be very careful to pull them apart. So when I was an undergraduate, back in a long time ago, I read Hennessy and Patterson, and the opening parts of that book talk about benchmarks and their role in computer architecture, but more broadly. And the point they make is that benchmarks can only ever be indicative. And if you have, and they tell an anecdote of a story of someone wanting to, maybe buy a database from either one vendor or another. And their point was the benchmarks might give you an idea about which of those databases is going to be better, but you as the customer, ultimately the only way you will know is if you deploy that database on your system with your constraints, with your workload. And so as a consumer, that's ultimately the only thing you can do. And benchmarks up until that point are only ever going to be indicative. Yep. So that I just want to make that really clear. I think we all know that, but I think it's worth saying that again. So there's a distinction between what you need in deployment and what a benchmark will do and what purpose a benchmark serves. Now, as far as Java goes, Java's been pretty well served by benchmarks compared to many of the other languages in the programming languages community. And as you know, we welcome contributions. So if you would like to contribute any of those things, the Da Capo project would be super happy.
Great. And I think the community, I mean, let's make sure that everyone in the community hears that that's not just an invitation to me, right? This is an invitation to anyone to work on this.
Absolutely. Yeah. And it's on GitHub, and pull requests are very, very welcome. So if we can improve those. So 100%, and I should have started by saying thank you very much for raising this, because I think this sort of discussion is certainly absolutely useful, both with respect to benchmarks, but also with respect to methodology. And I also want to point to one news paper from OOPSLA last year, one news is sitting right there, which talks about almost exactly this question, and how to deploy, how to build a GC for an industrial, a hyperscaled service at Google. And how a benchmark suite like Da Capo, which has got holes, it's a very widely varied benchmark, how that can service that, and how to address almost exactly the problems you're talking about. So that was published at OOPSLA last year, and if anyone wants to talk to Wenyu about that, he's sitting right over there. So I think that's worth noting. But the other thing I want to point to here is that the GC community is broad, and Java is a very important part of it, but it's only one part. I personally work on 5 different production runtimes. But I spend my working life working on 5 completely different production runtimes: Android, Chrome, the Ruby GC, the Julia GC, and OpenJDK. 5 different systems, and they're wildly different. And this touches on one part of the GC environment, but more particularly, it touches on the part that considers large-scale deployments. Now, large-scale deployments both cover compressed pointers, which is actually the majority. So 80% of large-scale services are actually running with compressed pointers. That means they're running in less than 32 gigabytes of total heap size. And those that use uncompressed pointers are probably only 20% of the large-scale service deployments for Java. So if we think about situations where the actual physical, where the heap sizes are bigger than 32 gigabytes, that's a very important space, but it is only a small part of the space of GC environments. So I just want to make sure we're totally on top of that. The other point is, and I guess perhaps the most important part, and the thing that worries me most about everything we heard, was the question of the economics of ignoring the baseline. Okay, so what the min-heap is doing is saying, look, if pressed, we could run this particular workload, whichever workload it is, in this available space. And when we deploy it in a particular situation, it's very, very important to know that we're gaining a certain performance at this amount of cost relative to the baseline. And if we discard the minimum heap baseline, then we're not looking at the efficiency of that particular GC with respect to memory. And I think we can't dismiss that. So what because all of us as scientists are concerned with efficiency, and efficiency means measuring against some baseline. And so if this thing here can run in 2 gigabytes and we're using 64, we've got a 32-fold overhead.
So can I get a word in sideways?
Yeah.
Thank you. I'm nearly done, I mean, I agree with that, but I also think that when we are running with the smallest possible heap, we're only looking at memory, and we should be looking at both memory and CPU.
Absolutely.
Right? And I think that when you're looking at you can sometimes get an on-par result with two collectors, but then one is using 2 or 3 times as much CPU, or suddenly the benchmark with 400 cycles per second is spending 80% of its time doing GC and not doing the actual program, right? So I think if we want to bring costs into the space, we also need to consider that CPU also has 100%. Costs, right?
And I just point out that I think Jonas overlooked the great work done by Zessi and Kai back in with their elbow work, which looks at exactly this thing, how to measure the CPU cost of a GC. And it would have been good if Jonas's blog post mentioned that when he wrote that blog post, because that covered this in great detail, how we measure the cost of the CPU. So of course, I think everyone in this room knows that GC is a time-space trade-off, and we need to measure both, absolutely. But I'm nearly done. But there was a lot in that talk, and I just wanted to respond to it. So I just wanted to point out that we need to ground ourselves in what our costs are, both with respect to CPU and with memory. And if we don't understand the minimum heap size, and we go ahead and use 32x or 16x, the minimum heap size, then we've got an overhead there. And at the moment, most of the industry is facing a huge DRAM crunch. DRAM is not free. It may be marketed by cloud services as apparently being free, but in most cases, it's actually, we don't get the whole machine to ourselves.
I agree with that, and that's why I'm proposing that we sweep down from a representative heap size rather than sweeping up from a minimum heap size.
Representative size with respect to your deployment space, and I think if you want to write a paper, any one of us wants to write a paper because we're concerned, say for example, when you use paper, with a particular cloud service with a particular available memory, that's absolutely the correct thing to do. Yeah. But we shouldn't do that without forgetting about how much we're paying in memory. That was it. Look, I will stop at this point because everyone else needs a chance to ask questions. But I want to say thanks again for raising this. But I would say that the prescription of ignoring the bottom line of how much memory the thing would take compared to how much you're using is extremely dangerous, particularly in an environment where DRAM is as expensive as it is today. And also finally the point that this is one part of the GC space, and there's a huge amount of other places where memory efficiency is the absolute premium, like on the phone and so forth.
Thanks for the question.
Hi, you have said very little about pause time and latency. Do you not consider it as important as throughput?
Quite the opposite, but that would be another hour. So I mean, we had some latency scores in the spec results that you have seen, right? I briefly showed the Cassandra latency result as well, but that's an entirely different bag of tricks, and I wanted just to have, let's say, a crisper story for this one. I'm happy to talk offline.
Hey. Thanks. So great talk. I'm Wenyu, and I'm the X author here. So can you go to like slide 40?
40? Yeah. Yep. Let's hope so.
Well, so I'm just having a minor question about like how representative those.
Is this slide the slide that you want?
Yeah.
Yeah. Excellent.
Well, I'm not going to ask anything about the XR. So the I'm just wondering like how representative are the 4 heap factors here, and
sorry, how
well,
can you speak?
well, I'm just wondering like how representative are the 4 heap factors here, and like what's actually mean by like calculating the mean over the 4 data points. Like to me, like for example, if you remove like 1.3x and adding like 20x,
Yeah.
the conclusion can totally change.
Oh
Like,
yeah,
for example,
totally,
XR
totally.
can be
Yeah.
consistently worse than G1.
I do believe we picked up this technique from your paper, actually. So I agree.
Well,
Yeah.
I'm picking the 3 heap factors for like scalability analysis. I'm not
Yeah.
intending to like calculate.
Yeah. Oh yeah, totally. I mean, I guess I should have a snake oil on this picture as well, because of course, just like I can control my results by choosing between default and large, I can also control my results with what heap factors I'm choosing, right? And I think that's really what this is all about, in a sense.
Yeah, okay, makes sense. Thank you.
Okay, let's thank to the speaker again.
Thank you.
To be by Mark Maron on going where no GC has gone before.
All right, thank you for the introduction. Exciting, yeah. So my name is Mark. This is some work that I did with Anthony over here. He's an undergrad researcher, did a lot of great engineering on this project. So, you know, feel free to say hi to him if you have any questions about this. So, as the title says, this is a memory system for Bosky. And this is not just, this is the programming language we were doing, but you know, a key part of this work is not just building a garbage collector, but what can you do building a garbage collector if you think about building the language as a co-design process, right? So I want to start off talking a little bit about what Bosky is and some of the features that are going to be particularly relevant to this whole concept. So at a high level, it's kind of a programming language and stack that was designed and optimized for reasoning. And when I say reasoning, what do I mean? I mean saying, if I give you a chunk of code, whether you're a human, you're a formal tool like a theorem prover, or you're an AI agent, we want to make it as easy as possible for you to look at that code and know what it can and can't do, right? What is it going to change? What is it not going to change? What is the output going to look like? What parts of memory is it actually going to touch, right? Now, usually when you come to an academic talk, the talk says, I have a cool new idea for a new feature or a new analysis that I'm going to take and I'm going to put on a language. I'm going to stack something bigger on top of this and add this on. Well, we take a totally different view, right? My version is we're reaching a critical point in programming languages. We have this sort of JavaScript, Java, Python family of languages that have been around for as long as I've been a computer scientist. We've added more and more features, and they're just starting to creak. And we're at a point where there was going to be a new paradigm shift to new ways to think about programming language design. And this is kind of Bosky's a stab at that, where we try and tear out anything that might have made sense 30 years ago, but just requires some rethinking today. So we're going to simplify everything as much as possible. I'm not going to add anything new. I'm not going to solve complexity by adding new complexity, and we're going to see where that gets us. So what do I mean by simplify? I don't mean I'm only going to have one keyword or there's one operation that does everything. What it means is I'm going to look at foundational sources of complexity, maybe accidental complexity or implicit complexity, that just seem to complicate life when you're building a compiler, when you're building a runtime, that every time you have a research project that starts out with a great idea and then you're like, oh gosh, we're doing loop invariance again, right? And everything runs into a wall. So there are four big things that we got rid of in Bosky in the core. No loops, right? It's immutable, fully referentially transparent, pure, right? So it's very easy to reason about, no frame rules, no non-monotone reasoning, no inductive invariance on loops, all that good stuff. And two key things for this talk: it doesn't have you can't build cyclic data structures. It's impossible in the design of the language. And the semantics are fully deterministic. So there is one and only one possible output for any computation, guaranteed, right? And the other thing we do is we just try and make as much information explicit that's usually implicit. Like if I'm looking at a C code base and I want to call a function or create an object, I need to kind of wonder, like, what is the implicit invariant that I need to preserve about this object in order for something to not blow up elsewhere? And so I need to look at out-of-date documentation, try and find the coworker who wrote that code a month ago, rummage around the code base and guess. We want to take all this implicit knowledge, put it in a very explicit form that is compiled and put right in the source code as a first-class artifact. So there are a lot of words here, but let me show you kind of just a little bit of code. So here's one example. Even though we have this very nice functional core, the goal is to make this very accessible to a modern dev coming from TypeScript or Java or something. So here's an absolute value function in Bosky. It's not functional. Even though the core is functional, we have block structures, we have variable reassignment. Developers want parentheses, give them what they want, right? Make them very happy. You can see we make this implicit information explicit, ensures, requires, inductive data invariants are all part of the syntax of the language, but it's very natural for someone who's a modern developer. We have a lot of nice affordances like spread and rest, higher order functions for doing data processing over collections rather than writing loops with off by one errors and all this stuff. So pretty nice language there. And we spent last summer, we wrote around 25,000 lines of Bosky. We were like really excited about this. We're like, okay, let's build this and actually start getting some users and start really pushing forward with this. And that means we need a GC, right? We can't use a slow interpreter and just rely on the JavaScript collector anymore. So I'm coming from, you know, cloud dev experience. I spent a lot of time working on Node.js, working with folks in the JavaScript team at Microsoft, seeing all of this community, the serverless folks, what they were doing. And I noticed kind of some differences from what I would call classical GC systems, where it was a huge machine and the emphasis was really on throughput of batch processing and jobs, right? In this space, people were really worried about startup. Like, I'm scaling out rapidly. I need my applications to start up very fast. I'm responding to short user requests, so latency is critical, right? Like, my 95 or 99th percentile is more important than getting the max throughput of the system, right? Because that's where I lose customers when it takes 2 seconds to respond. And of course, memory footprint. I'm scaling out, I'm packing a bunch of these things on a machine, and of course it costs an extra $1 for each machine and each extra VM I spin up, right? So this was kind of why I wanted to think about, like, let's optimize the GC for this. And interestingly, this is also seeming to become very important for agentic style applications that have a lot of this rapid scale up, scale down behavior. And of course, you know, the interesting thing for me is a lot of times when you think about building a GC, right, there's this sort of, I have 3 things I want. I want good latency, good throughput, and no starvation. But there's trade-offs between these, and if I optimize one, I lose on another. So I kind of have to, I want 3, I choose 2, right? And conventional wisdom kind of suggests that that's just the way life is, and you sort that out. Now, interestingly to me, when we were getting started on this project, there was a paper at Uppsala Splash last year that they had a little proof that says this is not just a gut feeling, but this is in fact theoretically impossible to have all 3 in a language that has both mutations and cyclic data structure. So it's sort of an impossibility result for any existing language, almost any existing language today, that you could have a GC that satisfies all 3. But conveniently for us, Bosky actually is immutable, so no mutation, and cycle free. So the question is, can we do better in Bosky, right? Can we actually build a GC that satisfies all of these desirable properties simultaneously? And, you know, spoiler, or maybe not a spoiler because I'm giving the talk, yes, we can, right? So how do we do that, right? That was the next question. And I thought back to a couple papers that I really liked from, wow, 2023. That's an autocorrect, it's not right. From 2003. Both of these papers are from 2003. And they both talked about a similar idea. And it basically boils down to this. If I look at how object lifetimes go along, I kind of have young objects that are very hot, allocated quickly, touched a lot, die young, right? And then I have older objects that hang around for a long time, get kind of cold or touched infrequently, and will probably live for a long time. And with this sort of bimodal behavior, does it make sense to use the same collector algorithm for both families of objects? And the answer was no. Let's try and pick a collector that works well for the behavior of each class of objects, and then put those objects in that part of the heap, right? So we use copy and collector for the young nursery, and we use RC for the old space. And this seems like a great setup, and very cool. But the results were good, but not phenomenally better, right? And kind of the problem was, well, your latency gets better because you aren't doing a bunch of old heap traversals, except every now and then, since RC can't collect cycles, you need a backup cycle collector that does need to traverse the whole heap. So on average, your latency gets better, but you still have a high 99th percentile latency when that cycle collector has to kick in, right? And you get better mutator throughput, but you still have some slowdown because those RC objects, although they usually aren't touched much, sometimes you have a bit of code that goes and does a lot of mutations on old objects, right? which require a bunch of RC updates and a bunch of memory, remembered set entries, because you now need to reprocess these, and then you have a larger young processing time. So you things are better, but they're not awesome, or as good as you might expect. And this this line of work kind of hovered for a while. So what do we do? Well, now we know we have no cycles and we have an immutable set of objects. So the question is, how do we take these existing algorithms and how do we not add a cool new feature to them, but how do we simplify them and eliminate all of these extra complexities and actually get them down into their high performance essence, right? So we want to go a little further, because I just kind of like conservative root collectors, because I'd really like to set this up where the mutator, the application code, doesn't have to worry about interacting with the GC code almost anywhere except where it wants memory, right? So we're going to do a conservative root set, so we don't have to do stack maps. We don't have to worry about pointers to internal references, no safe points for synchronizations if we have multi-threaded collectors. And in fact, each thread can sort of run its own allocator and most of its collector entirely independently. So this allows us to scale up and scale down on threads, I think, a lot nicer. We haven't really evaluated that yet, but I'm optimistic. So it's a really simple algorithm once you've distilled and simplified it a lot. So I'm not going to go into a lot of detail, but I'll just walk through an example so that we all are on the same page. So here we have a heap. We have a set of roots. They can point back to themselves. They can point to some young objects, some old objects. Young objects can point to old objects, but since we can't mutate old objects, we can never get any old to young pointers. So we don't need any remembered sets. We don't need any write barriers or anything, right? This is great. It makes our life a lot easier. So for collection, we start from the roots. We go and we mark the young objects. Anything that's young, we'll mark and get ready to evacuate, but we don't need to walk any of the old objects because they're all reference counted, so we just stop there. So the only thing the mark and evacuate phase has to do is touch the nursery. Then we go ahead and evacuate all of those young objects. Since we're a conservative scan, if we're pointed to by a heap object, we just have to promote it in place. If it's only pointed to by objects from other, or pointers from other objects, then we know those are precise, so we can evacuate it, so we get the benefits of most of the benefits of a copying collector and compaction and memory reuse. We'll go and do our RC increments on all the objects now that they're in the old space, and then all we have to do is go ahead and reclaim the young space and do any RC decrements, and that's it, and our collection's done and we're ready to allocate again. So very simple, not too hard, still managed to have plenty of bugs in there. It's garbage collector code anyways, always, so there's always fun bugs. But the interesting thing is, the thing that's really cool is, we can have it all in a sense with this algorithm and this language. So we're guaranteed bounded pause times, because we will only, on a collection, we'll only have to go and sweep the young space. And we don't have any remembered sets, so we don't have any extra stuff that the mutator can create extra work for us, right? So our pause times are bounded by that young space collection. We have a pretty high throughput because we aren't touching objects repeatedly, right? We aren't going to basically mutate an object and then have to rescan a whole part of the heap, right? Or we don't have to do repeated RC inks and decks because we're traversing some part of the old heap, right? We only do inks and decks proportional to the number of allocations. We're free of starvation because each collection will collect all of the nursery plus whatever was released in the RC space. So we're guaranteed to get enough memory on each collection to satisfy all requests until the next collection. We can never be outrun by the mutator. And the other great thing is, since our heap, the old RC heap, is basically, anything that's alive in there has to be used by the application. So that's tightly bounded in the amount of memory overhead. And then the nursery is a fixed size, in our case 8 megabytes. So we don't have to do a 1x, 2x, 4x of the live heap size, right? The amount of heap we use is the live heap size plus the constant nursery overhead. So we have a very efficient memory footprint in the collector memory usage, okay? One thing that I thought was also very interesting about this is when the collector runs, since it only has to scan the young space and then touch objects in the old space that were referenced by young objects, we only touch the young space plus this old space fringe. So the collector will never go and traverse large parts of the heap that are cold and thrash out whatever objects or memory locations the application is touching. So we get a very nice memory pressure happiness result there as well, that we never thrash the application cache. So this was very, very cool, sort of a bonus feature. Okay, so theoretically this was all very nice, but we wanted to do an implementation to validate that in practice things matched, right? So as I said, our goal was simplify. So the allocator implementation, collector implementation is actually pretty small, about 2.4 kilolines of code. Not very optimized yet. They're just standing it up, so lots of room for improvement. Still bugs. I was fighting one yesterday, but enough confidence to run things. Our default configuration is an 8 kilobyte page with an 8 megabyte nursery fixed. We're running this on an AMD, with 64 gigs of memory, so plenty of space there. Now, one of the challenges of this language in runtime co-design is you've got a new language. It doesn't have a lot of code established. So our benchmarks are a little small, so I don't want to oversell this as a definitive result, but I think it's indicative that the theory and the practice are consistent, right? So our benchmarks range from about 200 to 5,000 lines of code written in Bosky. When we run this, the GC overhead's about 7% overall. We kind of tuned for that. So not great, but pretty decent. And we have these benchmarks. And as you can see, if you compare our collector Pando with an Epsilon GC, which does no work, we are actually much faster because we get far much better cache locality, but a good sanity check that the cost is not crazy. But to me, more importantly, is the pause times that we see in the collector at the 50th percentile level are very small. This is in microseconds. But also that they stay very constrained going up to the 99th percentile. So we see a very low, sort of variability in this behavior, which is exactly what we wanted for nice, predictable performance in the overall application there. Now, we did want to do a little comparison with an existing Java application. Now, we went to NBody, which has everybody's favorite benchmark, binary trees. Everybody uses this. It's one of the great JavaScript benchmarks. And basically, it just creates a lot of binary trees, some that live a long time, some that die along quickly. It's designed to stress the garbage collector. And the nice thing is, you can write exactly the same code in Bosky and in Java, so it says apples and apples comparison you can get, even if the benchmark is a little simple. But at least it gives us a sanity check. So we went and ran this benchmark with ZGC, Shenandoah, and Pando. Now, as you can see, if we turn the heap up to an unlimited amount for whatever the application wants to use, Shenandoah and ZGC are much faster on this. They take about 2.5 seconds. We take about 6 seconds. So clearly, our GC is not as performant as these very engineered, well-engineered and optimized systems, but at least not embarrassingly slow. Now, what was interesting here is, one of our claims was that our memory footprint, our resource requirements were very constrained, and we did not see significant performance degradation in that constrained runtime. So we turned the min heap down to 1.5x to see how this looked. So for our system, behavior is totally unchanged, right? Because it is, the memory it needs is the actual live heap plus that overhead given by the nursery. So we perform just as well. Whereas ZGC and Shenandoah obviously struggle some more, right? They hit these limits very hard. They run into degenerate collections. Their latency goes up, and they have to spend multiple threads, to get collection to keep the application from starving. Now, the wall clock time still outperforms us, like 4.7 to 5.9 seconds. But if you look at the CPU time, you can see that they've really pumped up the resources to do these massive parallel collections, right? So it actually, the cost is pretty high. Okay, so what to take away from this? Well, I think one thing is, hopefully you say, oh, this is a cool GC and a cool language. I think it's really neat to see that you can avoid some of these impossibility results by not just trying to engineer more in the GC, but think more broadly about the ecosystem and the problem. So that kind of leads me to the second thing. I think this is maybe, this result I hope is exciting to you, but I think also maybe this encourages the community to think a little bit more about what the space of language design is and how it opens up more possibilities for runtime system development. I think this is a really interesting time, this disruption of LLMs and the need for people to write languages that support not traditional workloads, but these LLM, AI, agentic style workloads. And I also see this as an important time for our community to kind of step in and, in industry, oftentimes a problem comes up and it needs to be solved in 3 months. And that means it's time to grab whatever is there and make it work. And what I would hate to see is for people to grab JavaScript, put a new coat of paint on that, and us to be stuck with that for another 30 years. So I think this is a great opportunity for us. This is a crisis point in programming languages for us to step in and actually show some interesting points in this design space. So when people need to grab stuff, there are good things for them to grab and build a future that allows us to be innovative and creative and really where we want to be. So I'll wrap it up with that, with a couple links to some of these papers I mentioned, and a link to the Bosky language programming repository if anybody wants to poke around or take a look at stuff there. And I think I have a couple minutes for questions.
A couple of minutes for questions. So I have a question. So when you're doing the collection, isn't it possible that you could end up collecting a lot of the old heap? Because if a lot of it becomes unreachable at that.
The RC space? Yeah, so what we do is we basically have just a little, we time box that and then have basically a pending deletion list that we thread through there that we will then heartbeat off. So we will gradually reclaim the RC space. If you have like a catastrophic deletion style thing, yes.
Hi, I just wanted to point out some super cool work by that guy over there, Matt Parkinson, about basically doing reference counting with immutable cyclic garbage. So you could be able to have free cycles in your Bosky language and still, I think, retain many of these properties, right? You do a nice SCC analysis of all the objects that are connected together in an immutable cycle, and they have all the same lifetime. So that would be an interesting opportunity for you to possibly look at that work. Yeah, for sure. I think our goal here was just get a plausible baseline to validate this. But we definitely have some stuff in terms of better SCC collection, in terms of better multi-threaded collection, and we'd also like to do, there's always an issue of fragmentation, right? Especially since we have a conservative stack. So can we basically use similar ideas of leveraging features of the runtime to be more aggressive in doing our compaction on this on fragmented objects, right? So specifically, we have this very nice feature that things are fully referentially transparent. So you can't tell if you point to the same object or different objects. And so in a sense, if we don't have this concern of atomicity, so we can basically move an object, forward your pointer, and it doesn't matter if you have 2 copies of that object, eventually we move them together, you're confluent in your rewrites, and you don't care. So we don't have to do a bunch of atomic coordination. So we think there's a lot of other interesting possibilities here that we definitely want to explore once we just sort of bootstrap up a little bit. Yeah.
Time for one very short question for those who've left. No, then let's thank Mark. Okay, so our next talk is going to be given by Nicholas van Kempen, and it's going to be on reconsidering a classic paper on reconsidering custom memory allocation.
Testing is working, okay. All right. Thank you for the introduction. This is joint work with, I'm Nicholas, and this is joint work with Emery Berger, and we're working at the University of Massachusetts Amherst. So let's start this talk by rewinding the clock 24 years back to 2002. And so some events are familiar. In 2002 was a multiple of 4 years ago, and there was a World Cup. It was co-hosted by Korea and Japan, and depicted here is the opening game of France and Senegal, which Senegal famously won 1-0, eventually leading to France being eliminated before they even made it to knockout stage. So on the technical side, your favorite search engine might have been Yahoo. So for the nostalgic, there's in June 2002, sorry, this is what Yahoo looked like. I was 4 years old, so I don't actually remember what Yahoo looked like, but this is what it did. And so on the OS side, your operating system might have been Windows XP. It came out in late 2001, and 2002 is really when it became widespread. And so your desktop might have looked like this. If you were Team Apple, or you were looking to buy an Apple computer, this is what the apple.com website looked like. And so you might have been browsing on this eMac, which is advertised at $1,100, which if you convert to today's money, surprisingly, is actually around $2,026. Coincidences. So if you're on your $1,000 eMac or your Windows XP computer, looking for academic papers that are memory related, searching on Yahoo for those papers, you might have stumbled upon this paper named Reconsidering Custom Memory Allocation from Berger, Zorn, and McKinley, which was published at OOPSLA 2002. And so a common software recommendation in 2002 was to write your own custom memory allocator with the expectation that it would outperform the system default. And so this paper was reconsidering that expectation. And in fact, they reconsidered it so well that it won most influential paper 10 years later, again, from OOPSLA. And there's a few, while receiving the award, there's this citation with a few relevant words here. So until 2002, it was taken for granted that application-specific memory allocators were superior to general-purpose libraries. And so what that paper did is, reconsider that expectation and found that that assumption was not well-founded, and that in at least some cases, the general-purpose allocator was actually able to match or outperform handcrafted allocators. So let's take a step back and see what exactly we're talking about. So we're talking about mostly, again, native languages, so C, C++, Rust. And here's a snippet of a C++ function, a very simple snippet of what a function might look like. So it'll first allocate n objects of a certain size, do some kind of processing, and then free those objects. And there's two costs that are associated with these operations. There's costs that are associated with these operations, and highlighted here are the costs to actually allocate the objects and the cost to actually free the objects. And those were the two costs that people mostly focused on, at least back then, because they thought that those were the slow parts of the programs. And so Emery's paper, Emery, Benjamin, and Catherine's paper, basically talked about the strategies that people were using to actually make this faster. And so they placed these custom allocation strategies in two general buckets: per class allocators and region allocators. So now I'm going to give a brief overview into what each kind of these allocators are. So first, per class allocator, like the name implies, is per class. So every time you have a class that you want to use it for, you need to write your own code to enable it for that class. And so even in C++, which makes it a little bit easier because you can override new and delete, there's still a pretty high engineering cost to it, right? For every object, you have to write your own code. And so how it works is, first, you have a free list. Typically, those work with a free list of recycled objects. So you need a head node and then pointers to the next node. And then first looking at free, what happens when you free? Well, instead of freeing and returning memory to the underlying allocator, it'll instead push it on top of the free list simply. And then when you allocate, well, if you didn't have anything on the free list, you'll have to revert back to malloc. But if you did have a node ready to be recycled, then you can just use that instead of having to allocate again. And so one thing to note with this strategy is that the actual number of new and delete operations doesn't change. You call the new the same amount of times. What does change is how many times you actually call the underlying malloc or free. And so again, at the time, people thought that that was the expensive part. And so people thought that, well, if we avoid calling malloc, we'll save some cycles. And so that's the idea behind per class allocators. Now, let's talk about let's talk about the second family, main family of custom allocation strategies, which are region allocators, which actually we'll see in this talk a little more interesting. They're also called arenas, bump pointers, chunk allocators. And so again, I have this simple C++ snippet which allocates n objects into a vector. This monotonic buffer resource is the C++ name for region allocation. They couldn't make it simple, of course. And so essentially how it works is when you call malloc a first time, instead of only allocating a single object, it'll allocate a bigger chunk. And so in this case, it looks like there's space for 2 objects. So on the first malloc, it'll allocate a size for 2 objects and only return to you the first slot in that chunk. The second time you call malloc, it'll give you the second slot, right? And then the next time you call malloc, it'll allocate a new chunk, in this case, maybe even bigger, and again, give you the first slot, and so on and so forth, right? And so essentially, it chunks allocations as it goes. So how do you free with this strategy? You don't. So this is where the main trade-off is. You essentially don't free until you're completely done using this arena and until every allocation is basically ready to be disposed of. So if you can't free individual objects, how do you reclaim the memory? And so this happens in some kind of either reset function or in the C++ snippet that I put up there, it happens at destruction of that buffer resource. And so essentially, it frees all the chunks one by one. And so one thing to notice here is that there is actually a reduction of operations in this scenario, because instead of calling, let's say you had 10 objects, let's say over 2 chunks, instead of having to call free on 10 different things, you can actually call free twice, right? And so you're saving a few on these reduced operations. So again, Berger, Zorn, and McKinley looked at these 2 strategies, and they concluded that, well, for per class allocators, it wasn't any better than general purpose allocation or naive allocation, meaning, again, just calling malloc free directly. While region allocators actually could provide some benefits, and in 2002 it was up to 44%. Now, enough talking about the past. Today is 2026, so some things have changed, some things have stayed the same. In fact, it's still the World Cup, and France is playing Senegal in their opening game today at 1 p.m. So I'm not sure who's talking at 1 p.m., but I expect all of you to tune in the game instead. Your favorite search engine, Yahoo. Let's be honest, no one uses it anymore. Everyone has moved on, and everyone uses AI to search for things nowadays. So here's a picture of the Claude, window. And of course, again, on the technical side, there's been a lot of updates to software, hardware, etc. So the original study uses a Pentium processor with 200K of cache and 300 megabytes of memory. Of course, today that'd be absurd. So we update this with a modern processor with modern cache sizes of memory, 200x the cache size, and 400x the size of memory. Allocators have also changed a lot. So at the time, the baseline was the Windows default allocator, labeled here Win32, and the state of the art was dlmalloc. And today, what we use as the baseline is the Linux default allocator, here glibcmalloc, and we select 2 high-performance state-of-the-art allocators, jemalloc and memalloc. And one fun fact is that actually, dlmalloc, through a series of evolutions, is now today the Linux default allocation. So what was the state-of-the-art then, kind of, is now the baseline. And then finally, we extended the original study with a few more benchmarks, namely from Clang and Blender, that represent modern workloads. So what do the results look like today? So first, per class allocators. So again, in 2002, didn't really matter. Well, we kind of joined this conclusion. So on this, so our conclusions roughly match those of 20 years ago. So on this highlighted benchmark, for the best allocator, which in this case is memalloc, we see that per class allocation only gives you a 2% improvement, which is pretty little. And again, this is considering that the actual cost of implementing these per class allocators is very high. So high cost for 2% performance improvement, not really worth it. And so we actually extended this and calculated an upper bound. So how much can per class allocators even possibly save you at all? And so this is what it looks like. And so if you focus on the high performance allocators, again, jemalloc and memalloc, at most these per class allocators will save you roughly 10%. But again, this is on a micro benchmark who spends 100% of its time basically allocating and freeing. So if you were looking at a regular program, that spends 5 to 10% allocating and freeing, you're actually going to drop an order of magnitude more towards 1 to 2%, which is kind of what we're seeing in this box and benchmark. So expectedly maybe, 2002 conclusions still hold. Per class allocators are not really worth it still today. Now, switching to the region allocators, well, did that change? So in 2026, the speed up for region allocators is up to 14-15% on 2 benchmarks, which is still relatively significant. Because again, especially again comparing the engineering cost, it's lower for region allocators than these per class allocators. However, it's worth noting that the general purpose allocators have significantly caught up, right? In 2002, speed up was listed as at most 44%. Today, it's only 15%, which again, 15% is significant, but obviously it's less than 44. And so far we've talked about basically 2 costs, right? We've talked about the results for per class allocators and for region allocators, and those results were mostly focused on the cost to allocate things and the cost to free those things. And in fact, there's one more cost to running with manual memory management, and that is, it's a little more subtle, is the cost of placement. And so let me explain what I mean by that. So when you allocate a set of objects with malloc, again, here's allocating, I think, about 10 objects with malloc, the pointers you get back from malloc represent a fixed region in memory. And so that fixed region is going to be the location of the object for its entire lifetime, and there's no way to change that or to suggest a specific other location. And so in this case, you hope that you'll end up in the left scenario where everything is kind of packed together, and it might fit in, let's say, 2 cache lines if you assume one row is 1 cache line, versus the second case where everything is a lot more scattered. And so if you were in the first case, well, the first case will inevitably lead to better locality, better cache utilization, fewer cache misses, and therefore you'll get a faster program. So obviously you want to be in the first case, but unfortunately, if you use malloc and free, you don't have that guarantee. You don't know, things might end up in either one case, and you have no control over that. And this is where region allocators can actually help, surprisingly. So again, here's a short snippet allocating n objects into a region allocator. And by construction, these objects are going to be packed together, right? Because region allocators have this mechanism of chunking allocations together, the objects will end up close together in memory. And so again, on top of the reduced operations, this is the second benefit of region allocators. They have these locality and contiguity guarantees. Now, here's the problem. How do you actually highlight this benefit, right? And so one problem that we found is that some of the benchmarks we used were short-lived. And so because they're short-lived, they don't actually experience a relevant level of fragmentation that, for example, long-running programs might. And so on this quick figure, you see whether you use naive or region allocation, if you start from a blank heap, meaning there's nothing there, things will be contiguous anyway, right? So in this, if you're just naively doing this, you're not going to highlight that contiguity guarantee that region allocations bring. So how can we highlight this property? Well, we developed this methodology that we named adversarial allocation, and which essentially is about putting garbage on the heap before the program starts. So we put garbage on the heap, which prevents the allocator from actually putting things anywhere at once. And so you can think about it in a way similar to long-running programs, which might have a variety of lifetimes, and so things, objects might be interspersed between each other. And so here's a simple example. In this case, there's only 2 garbage pieces. And so what we also are able to do is increase the level of how bad does this fragmentation, can this fragmentation be before we start the program. So here's a relatively small amount of fragmentation. We can increase it to the second level, which is about double the occupancy of garbage in this memory area, or we can make it very extreme, and in this case, most of the memory is actually garbage, and the allocator only has access to a few spots to allocate its memory. So what are the results? Well, if you were using naive allocation, like I said, there is no guarantee of contiguity. So therefore, naive allocation is very sensitive to these fragmentation problems. And so in this case, it's up to roughly 70% for the parser benchmark at the worst adversarial allocation settings. On the other hand, region allocators, again, by construction, are resilient to this, and so they're virtually immune to any changes, right? What was 70% in the parser is 0% if you just use the region allocator in that program. And so again, this gives region allocators a lot of predictability in long-running programs where you care about tail latency, programs where you want predictable performance. Region allocators are able to give you that. So yeah, they provide resistance to heap fragmentation. So to recap, we've talked about per-class allocators. In 2002, they were not really worth it. Well, today, still not really worth it. We've seen that on this, with the best allocator on that benchmark, it was at most a 2% win. So given the high engineering cost in the general case anyway, probably not worth it. Region allocators, they could still provide up to 15% performance improvements, obviously depending on the program. It's worth again noting that general purpose allocators have significantly closed the gap between what was 44% in 2002 is now only 15%. And we've extended the methodology with a new method called adversarial allocation, which allows us to actually quantify how much more resilient are these region allocators to fragmentation. And so we saw that what could be, in the worst case, is 70% degradation in a benchmark is actually 0 if you use the region allocator in that benchmark. So with that, I want to thank of my collaborators, of course, Emery, who's my advisor, and then folks from Bloomberg with who we've had a lot of productive discussions on this topic. So I highlighted Josh, Frank, and John, but there's a few more. And thank you guys for your attention.
Cool, we've got plenty of time for questions.
Thanks for that. Great talk.
Thank you.
I may have missed it. You may have explained it, but just with the per class allocators, how did you actually implement that? I mean, for these large benchmarks like Clang.
So we selected, good question. We selected benchmarks that already had custom allocators, and essentially we took them out.
Cool.
So we didn't actually implement the per class allocator. It's already there, and then we have either we keep it the original version or we take it out. Right?
Great.
Maybe LLMs can do a whole implementation.
Great talk, thank you. I'm surprised by the way you summarized the old paper, because looking at the abstract and the conclusions, it basically says, well, custom allocation is bad, except for region allocation, but, and then it said multiple buts. It said region allocation is hostile to common programming patterns. It's all sorts of bad things, and then both the abstract and the conclusions, they actually say that, well, the big thing is that we introduce REAPs, which are regions with the ability to deallocate a single object. So I was surprised that you didn't say anything about that. Can you say a little more?
Yeah, so correct. So first on the REAPs part, it's true. So the original paper introduced REAPs, which was a method to basically have region allocation while also trying to reduce the trade-off, which I'll get into in just a second, of higher memory usage. REAPs didn't really take off, right? You don't know about it today. And so that part of the paper was less successful than the part about reconsidering things. So it's true that in this talk I didn't mention the REAPs part, but it's true that the original paper does mention this technique. Now in terms of trade-off, yes, region allocations, there's a trade-off, right? I actually have an extra slide about that somewhere. There you go. And so the trade-off is, well, you have a much higher memory footprint, right? Because you can't free until you're done, you have a higher memory footprint. And so this was measured from the original paper, and that's not very dependent on the actual technique. It's more dependent on specific programs, right? Depending on how the programs use the technique. So this was the measurement in the original paper, and which would be the same measurement today because, again, it doesn't really depend on hardware. And I think the peak is that for one benchmark, using region allocation makes the peak RSS 3 times bigger, right? But again, if you look at that benchmark, its memory usage was like, I think 10 megs or something. So times 3, 30 megs, right? It's not that big of a deal. But yes, the trade-off is definitely program dependent. And for some programs, if you have lifetimes that are equal to each other, then region allocations make sense. And if you don't, then maybe it's not a good strategy. In fact, that's a future direction. What if you could automatically, maybe with an LLM, I don't know, suggest locations where, well, maybe this function is a good candidate for region allocation or not, right?
Follow up from Yannis's question. Maybe would it be true that one of the issues with the REAPs is that actually implementing it was a methodological hurdle for you? Because that would require some change. You explained in answer to my first question that the regions were already there. Implementing REAPs would have been a bit more non-trivial. Was that perhaps the blocker?
That's a fair assessment. I'd have to get back to you exactly on. I mean, REAPs hasn't been maintained basically since 2002, so there would also have been. I'd have to take a look at it again and see if it's actually implementable today, etc. Well, yes, maybe the other challenge is there's going to be more implementation work there, right?
Yeah, but I was thinking, we now have ways of addressing that toil of implementing it, so it kind of would be cool to see that.
Yeah.
So another question has to do with multi-threading. So clearly, better locality is great for single thread, but it's really bad when you have fault sharing among multiple threads. So did you evaluate anything multi-threaded?
Good question. So we don't have, so most of our benchmarks are single-threaded. And the issue kind of is with how region allocators are typically used. So they're actually used a decent amount in multi-threaded programs, but they're typically used in multi-threaded programs in per thread mode, right? So you'd have a thread that has a region and it only uses that region anyway, right? So in terms of evaluation, it actually doesn't make that much of a difference, at least in that scenario. And if you had a region allocator that was thread safe, at some point you're writing a general purpose allocators, the more you add to it. So so in that evaluation, it made sense to stick to single thread because of the way they're typically used, right?
Sorry, one last one. Again, a follow-up from Yannis's question.
We have time,
in terms of your contrast from the old times to now, surely that's one of the differences, right? Back in those days, many or most of our programs were single-threaded. Yeah, so many of our allocators were explicitly designed for single-threaded context, whereas now they have to be multi-threaded, right? And so that seems to like a really fundamental shift in that period that's relevant to your work, right?
Yeah. So you're right. 2002 is actually, I used to have slides about this, but it eventually took them out. 2002 is exactly when the shift kind of happened from single core to multi-core, and actually when people started also having a third level cache. Before that, it was only 2 levels, and so it's true. And so again, we looked at a lot of modern applications. Clang is basically single-threaded anyway, but Blender is multi-threaded, and again, it uses this per thread allocation. If you look at web servers, we were relatively unsuccessful in actually getting good measurements out of web servers because there's a lot of overhead in other parts of it. But web servers typically use custom allocators. For example, they have a region to process a request, and then when the request is finished, being handled, the region can just be disposed of. And so again, in basically every modern application I've looked at that use region allocators, it was a per thread, system. I don't think I've even seen one that was shared among things. So, but region allocators also give you these locality advantages, that would be an interesting direction in terms of evaluation. They give you the locality advantages per thread in a way, right? So you don't have false sharing, if ever your allocator was allocating things, interspersed and shared between threads, which most allocators don't do anyway, but again, region allocators provide you guarantees that this doesn't happen.
Time for one more question, which I could get mine in if no one else. So one example of per-class allocators that I've seen that does seem to be successful is in Python. So the Python objects, they keep around like 20 or 30 of every type of object. And the reason I think that one's successful is because it's keeping the objects already structured and already laid out and already like a bunch of initialization is done. So then when they recycle it, they just basically set a reference count and like clear a little bit of data. So I don't know if there's any cases like that you considered.
Good question. I didn't think of the Python thing. Good question. No, in terms of region allocation, actually I thought you were going to ask about the free list allocation, because in fact if you have the general purpose allocators makes a lot of use of these free list allocation in those scenarios. They actually make sense. But no, we haven't thought too much about. But it would be interesting. I'm interested to learn more about the region Python thing. So I'll look into it and maybe we'll have a chat later.
Okay, let's thank Nicholas.
Thank you.
Jeremy Singer, and I didn't see the last one.
Good morning. This is a presentation involving much ado about offset vectors.
That's...
In particular,
Hang on. Isn't it remote talk? This is when I should have prepared some jokes. We could have, but now we haven't got an... we could swap the talks round and try and get that lined up. So the remote one is... we could swap them if you want. Do the recorded one and then do the remote.
That would be great, yes.
Yeah, should we do that? Okay, so we're going to swap the order of talks for technical reasons. So the next talk is much ado about offset vectors, and it's Steve Blackburn and Hayley Patton, and she's going to be giving the talk recorded, and then Steve will be taking the questions. Cool.
it's about a kind of garbage collection. Good morning. This is a presentation involving much ado about offset vectors. In particular, it's about a kind of garbage collection algorithm which we've identified and named offset vector compaction. An offset vector compactor performs in-place compaction, and I'll first describe in-place compaction in order to explain why offset vector compactors are important. In-place compaction consists of three tasks, which occur after the collector has marked all the live objects. The compactor must compute a new address, called the forwarding address, for each live object. Ideally, it will do so in a way where all the objects will be pushed to one side of the heap, producing the most compact result. Then, the compactor updates all the references in the objects to refer to their forwarding addresses, and then the compactor relocates the objects to be stored in these new addresses. Unlike copying algorithms such as semispace, we don't need additional memory to perform in-place compaction. And unlike non-moving collectors, we still actively are defragmenting and compacting memory. Thus, collectors which use in-place compaction can be some of the most space-efficient collectors. But this abstract description glosses over that we need to somehow be able to map the objects to their forwarding addresses. And the way that we implement this mapping distinguishes many compaction algorithms from each other. The Lisp2 algorithm, one of the first compaction algorithms, implements this mapping by forwarding addresses by reserving a word before each object to store an address in. We assign increasing addresses to each live object, putting each immediately after the last object, plus space for the forwarding address. We update each reference to an object by reading the word before each referent object. We can finally then relocate all of the objects to complete the compaction. This algorithm works, but it has two main disadvantages. We first need to reserve space for each forwarding address. Now, in my example, I said there was a word to store each whole pointer. Some collectors are able to compress the address into the header by making them less than one word. But in any case, regardless of what size we end up with, we still need to have this spare space per object to store the forwarding addresses. We also can't reorder or fuse any of the passes together. In particular, we can't both update references and relocate the objects in the same pass, because we need the object and its forwarding address to be in the original location in order to retrieve the forwarding address given a reference pointing to the old address. So, could we somehow compute forwarding addresses on the fly without storing the addresses anywhere? Recall that we relocate each live object to immediately after, where we'll relocate the preceding live object too. Another way of stating this property is that we sum how much live data precedes an object in order to compute its forwarding address. This implies that we could just as well do a linear scan whilst forwarding an object, summing from the start of the heap to get to the start of the object. This algorithm would be heinously time efficient, but at the very least it doesn't require any space like Lisp2 does. This brings us to offset vector compaction. We can make this algorithm time efficient with little space overhead, not quite no space overhead, but nonetheless, we can introduce the eponymous offset vector, which captures parts of the sums that we were computing in order to reduce the amount of scanning which we need to forward objects. Suppose that we arrange for the tracing pass to set the mark bits for every live word in every live object, rather than just the first word of each live object. The mark bit map will then have marks for all the words which are live, and we're going to use this to compute the addresses later. The first pass of compaction is compute a running total of the live data, storing the total every so many words into the offset vector. And for the sake of brevity, we're going to call that every so many words a block. Then, to forward a reference to an object, we read off the entry in the offset vector for the block which contains the start of the object. And we add the live values, scanning from the start of the block to the start of the object. The sum of just those two values is the sum of all the live data which precedes the object, but computed in a different order. Storing running totals in the offset vector thus bounds each scan to just one block, and the scan amounts to taking a population count, which is a fast operation on contemporary processors. Another trick with offset vector compaction is that we only use side tables to compute a forwarding address, so we can update the references and relocate objects in the same pass, because we never update or invalidate these side tables when moving objects. This eliminates one pass from the Lisp2 algorithm, and also eliminates one frame which I would have to draw and animate. We make 6 contributions with our paper. Broadly, we introduce the taxonomy of offset vector compaction algorithms and review their history. We implement a variety of offset vector compactors, including the one-pass compactor presented at ISMM 24 by Corey and Petrank. We also introduce a new algorithm for computing the forwarding addresses based on a particular style of market bitmap. And we finally evaluate all of these compactors on a modern OpenJDK with a Da Capo benchmark suite. I've already given my introduction to offset vector compaction, so I'm going to talk about the history and design space of offset vector compactors, and then our results from evaluating a bunch of compactor designs. Now, the simple offset vector compactor I described before is almost exactly that used in OpenMCL, which was originally known as Macintosh Common Lisp in the 80s, renamed several times, and now it's known as Clojure Common Lisp, Clojure spelled with a Z. The first open source release of OpenMCL had this collector algorithm in 2001, but there are references to the algorithm having existed since 1996. Now, my simplification only actually left out that they extended the collector to be generational, which fits rather naturally with offset vector compaction. Offset vector compaction preserves the order of the live objects, so all of the old objects will accumulate near at the start of the heap, and the new objects will be allocated near the end of the heap. We couldn't find any mention of this collector in the literature, which is surprising as this collector is the first instance of offset vector compaction which we've found. The first 3 instances we found of offset vector compaction are the OpenMCL collector, the parallel old GC introduced in the Sun JDK5, and the parallel mark compact collector by IBM described in the paper named An Efficient Parallel Heap Compaction Algorithm by Aboudiad et al. The compressor by Komeni and Petrank builds upon the IBM collector, introducing the use of virtual memory remapping for parallel compaction and using page protection for concurrent and incremental compaction. The Android runtime then introduced a concurrent mark compact collector based on the design of the compressor, using the useFaultFD mechanism in Linux to handle page faults more efficiently than by using signal handlers and SIGSEG-V. Finally, the one-pass compactor, described in an intellectual abstract by Corey and Petrank, extends the compaction algorithm of the compressor with pointer threading based compaction to indeed perform all the steps of compaction in one pass. Now, I have some apologia for why we've invented another name for another set of algorithms. In my opinion, it's quite easy to look at this algorithm if you know the compressor and say, this is basically the compressor. But this neglects that the compressor wasn't the first offset vector compactor. If we're going by popularity, the Sun GC and the Android GC are also by far the most widely deployed instances of offset vector compaction. Furthermore, the idea of offset vector compaction is independent of using virtual memory mapping for parallel and concurrency. None of the other collectors we found are even both concurrent and parallel. There are good reasons for this, but still. The Android runtime, for example, does use a similar mechanism to the compressor for concurrent but not for parallel collection. It's more efficient on mobile devices to use a single-threaded GC, so there's no need to support parallel collection. The one-pass paper also suggests that you could use the mechanism with the one-pass compactor for parallel collection. But many collectors don't use that mechanism whilst still performing offset vector compaction. Some of the collectors fuse and also rearrange the compaction passes, further showing the breadth of the design space for offset vector compaction. We implemented various offset vector compactors in the memory management toolkit, including both the serial and parallel variants of the one-pass compactor. There are different parallel and serial variants, as the parallel variant introduces some synchronization needed in order to perform pointer threading with multiple threads, which we don't have in the serial version. We evaluate these collectors against the semi-space and IMIX collectors, which are the best performing canonical collectors in MMTK. And we evaluate them all on OpenJDK21 and the DeCapo-Chopin benchmark suite. All of the evaluated collectors are stop-the-world and full-heap collectors, and all but serial 1-pass are parallel. The parallel offset vector compactors partition the heap into regions of 256 kibibytes each for parallelization. Now, you'll notice that there are three, I guess I'll say, flavors of the offset vector compactors, indicated by the suffixes with a hyphen or lack of on each name, and these all handle the mark bitmap differently. The names without suffixes use a style of mark bitmap similar to the compressor, and unlike the example I gave before. They mark only the first and the last bits of each object. The names ending in CL-mol do the same, but they use a branch-free algorithm based on carryless multiplication, which we describe in the paper. The CCL suffix names mark all of the bits of the object, as Clojure Common Lisp does. All of the evaluation that we do is performed on a 16-core, 32-thread Zen 4 processor. We first evaluate our offset vector compactors against the canonical collectors in a parallel setting. All of the variants of offset vector compaction perform fairly similarly to these canonical collectors, but the branch-free variants have a clear performance advantage over the branchy variant. Both CCL and CL-mol variants approach, but are still outperformed by IMIX. But the vanilla OVC is closer to semi-space. Nonetheless, all of the offset vector compactors can run the tightest heaps of all the evaluated collectors. The two branch-free variants perform fairly similarly, but the CCL variant does slightly and consistently outperform the CL-mol variant. It's surprisingly slightly more efficient to set all the bits for all the live objects while marking with the CCL algorithm, rather than just the first and the last as we do with CL-mol. We assume that this is because the branch-free algorithm which we introduce in the paper for passing the mark bitmap in this style is slightly more complicated than just taking the population count as CCL can. Setting all of the bits is actually faster than it might sound, because you can set bits, whole words at a time, and all the objects tend to be quite small, so you're not actually setting that many bits at a time anyway. We then evaluate the parallel 1-pass against the parallel offset vector compaction. Surprisingly, 1-pass seems to lag offset vector compaction by a decent margin. So we looked and investigated what the causes could possibly be for the slowdown. We did so by using our serial version of 1-pass, which, if you recall, does not have this region-based design, and it also avoids all the synchronization needed for parallel pointer threading. We found that the serial 1-pass performs much closer to offset vector compaction on a single thread, but the parallel 1-pass, even though that's still running on a single thread, does consistently lag both. We then did a scalability analysis, which is better described in the paper, and found that the scalability of a 1-pass and the offset vector compactor is similar for all the thread counts in between 1 and 32 threads. This suggests that, as Corey and Petrank had suggested, the contention between threads is very low, but the synchronization mechanisms themselves are introducing a fair bit of overhead. We also measured how often either version of 1-pass resorts to using pointer threading. The parallel version, which uses the heap partitioned into regions, also performs more threading than the serial version, which doesn't. Likely due to these regions producing a different placement of objects in memory. Corey and Petrank suggest several suggested strategies for parallelizing the one-pass compactor. And it is possible that we picked an ill-suited strategy. In fact, the strategy we chose isn't in the one-pass compactor paper, but we thought it was a decently canonical one to have, so that's why we implemented it. Still, we think that implementers of one-pass will have to consider how parallel collection algorithms may partition a heap, and how the partitioning will affect the placement of objects in order to obtain the best performance from their collectors. Another issue to consider is that one might think going from 2 passes to 1 pass is a larger reduction in work than it actually is. At face value, halving the number of passes might suggest the collector somehow performs half the work, by some sense and measure. We ended up changing our informal language in the lab to compensate. We would say that the compressor really has 1.5 passes, which in some sense is a very strange thing to say, because a pass is a pass, and you can't only say it's a half. But the pass which computes the offset vector only has to traverse the side tables, the mark bitmap on the offset vector. And these have a combined memory footprint of only a few % of the size of the actual heap, and so they are less demanding on memory bandwidth. The other pass of the compressor, and some other passes of similar collectors, does traverse the actual heap, and also has to pass objects to update their fields and do more complicated acts. And subsequently, those passes tend to be an order of magnitude slower than computing the offset vector. This is all to say that offset vector compactors are a worthwhile subject to investigate. The lights in this room might disagree with me. I do think they are a worthwhile subject to investigate. Offset vector compactors are everywhere. Many Android phones, to this day, and Java users, admittedly up to JDK 23, but that's still pretty recent, they all use offset vector compaction. We found that offset vector compactors are competitive with the canonical algorithms, outperforming semispace and slightly lagging IMIX in our evaluation with MMTK on OpenJDK in Da Capo. We also found the one-pass compactor offers an algorithmic improvement over 2-pass offset vector compaction, but the additional synchronization in a parallel setting does still undo the speed-up provided by one-pass, even when contention is not an issue. So, thank you very much for your time. Steve will now take questions, as he is much more conveniently positioned on the other side of this screen. Goodbye.
So Steve's going to take questions. Questions?
So if I remember correctly, IMIX does reference counting as part of its internal. IMIX does reference counting as part of the main GC algorithm. No,
you can compose IMIX and reference counting. IMIX is just like the base algorithm, the canonical base algorithm.
My question
is just a tracing algorithm. Yeah.
So you showed the absolute numbers. I'm wondering if the metric that you should compare is like the number of relocated objects. Like the number of relocated objects. Because they might vary depending on the algorithm a lot.
Oh, absolutely. Yeah, so semispace will relocate every object. We didn't have here a good high-performance mark sweep algorithm. If we did, that's another canonical algorithm, which we would have liked to have included here, but we didn't have a good enough performing one to put in the evaluation, and that would move exactly no objects. Semispace and mark compact move all objects, and IMIX moves some objects. So yeah, they're distinctly different algorithms. The reason why we put them on the screen is because these are ones that people use as bases to make richer, more interesting algorithms. So hence their canonical base algorithms. So I think most algorithms today are some composition of mark sweep, mark compact, semispace, or IMIX. Most production collectors today use some combination of those, plus parallelism, concurrency, and and that composition. But yeah, they'd move very, very, very different numbers of objects, and there's an obvious trade-off to be made there.
Cool. Any more questions?
Yep.
So in the evaluation, I saw a lot of, for example, mentions to like using this on Android in part because of concurrency concerns. Is this approach also applicable on a server architecture with cores? Is there a reason it's better or worse than any other technique? What is the situation on?
It very much depends on the context. So Mark Compact is used by the old Sun or OpenJDK parallel collector in the old space, and it was originally an offset vector compactor. So it's very, very heavily used in serving computing and in Android. The comment that Haley made in the talk was that in Android, it's not parallelized, which is the difference with compressor. Compressor is concurrent and parallelized, but in Android, they're not parallelized. And the reason there is the deployment platform on a phone doesn't make parallelization of the GC profitable.
I have a quick.
Yep.
So on .NET, I know that it doesn't actually, so it does do that kind of compaction, but it uses the gaps between objects, so it moves blocks, or I think it calls it plugs. So a range of objects, and there's always a gap either side, and it keeps track of the offsets in this free space. So it's worked out which areas aren't accessible, and then it uses that somehow. I don't know if that's at all interesting.
It is interesting, and Haley did look at that, but I think it was a little bit hard. It's not very well documented, the algorithm. I mean, that's not a criticism. It's just not a published paper on it. So it was a little bit hard for Haley to really pin down exactly what the algorithm was. We would have liked to have done. And one of the, I think for me as someone who's been in the field for a really long time, I think one of the really interesting things that Haley did was discover these old implementations dating back actually probably before 2000 that did offset vector calculation. I, in my head, just thought of compressor as being the first implementation, but it's by no means the first. Yeah, we would love to have had that in the thing, but we just didn't have the information.
Cool. Okay, I think we need to move on to the next one. Okay, and in a change to the scheduled program, we're now going to go back to the interpreting memory safety via differential fuzzing with a cherry on top. And I think Jeremy is going to give a talk. Are we?
Not sure.
Excellent.
Oh dear. Yeah, because it looks like there's like a green light around their thing, but I can't hear them.
Yeah. They're on this right now, I think.
No. Nicole, we can't hear you. Can you hear us?
Yeah.
Oh dear.
Okay.
Yeah.
Oh.
Okay, Jeremy. Hello.
Hello.
It's Matt here, the session chair. I've introduced you already when you couldn't hear, so you should just start.
Oh, in that case, I will. Thanks so much. Good. Apologies for all the technical difficulties. Thanks for bearing with us, everybody. And yeah, good evening from Glasgow. Unlike lots of Scottish people who made it to World Cup in America, we're still in Scotland. But yeah, we're really glad to be able to tell you about our paper on interpreter memory safety via differential fuzzing with a cherry on top. So this is joint work between Kai and myself at Glasgow University and Huanting and Zheng at Leeds University. So just to give away everything in a single slide, we synthesized big corpus of Python code, which tickles the internals of the runtime. About 8,000 programs. Lots of them cause problems. And that was our intention, really, because we're looking for bugs in the runtime. And the particular runtime we're working with is MicroPython. We've got two separate builds of MicroPython. One is Cherry memory safe runtime, and the other is a non-Cherry conventional runtime. So we run the code on both and look to see what the differences are in the results. And at the end of the day, we find some real memory bugs in the MicroPython runtime. We found 51 bugs, 3 of which turned into GitHub issues and 2 of which have been patched. So I think there's a happy ending to our story. Yes, you might be thinking, why on earth do people have high-level language runtimes on microcontrollers? And here's an ESP microcontroller here. And I remember whenever I used to go to electronics classes and people would put up pictures of circuit boards, they always put a coin next to them. And I think it was to show the kind of relative scale of their circuit boards and so on. But actually, these kind of microcontrollers these days can be bought for pennies. They're really, really cheap. And they're very constrained hardware, you know, with kind of kilobytes of RAM and perhaps kilohertz processors. But even on such constrained embedded devices, people want to run high-level languages like Python and JavaScript and WebAssembly. This might be for accessibility, you know. Kids these days can only program in Python. It might be for prototyping, maybe to do some kind of rapid development of simple IoT applications. Maybe for memory safety, Python, purportedly, JavaScript and WebAssembly are memory safe in some sense. And maybe for portability, you can kind of move these higher level programs across different microcontroller families and architectures. But the point is, the underlying runtime is going to have to be a legacy C application that does have manual memory management. And that's exactly how MicroPython, the runtime we're looking at, is implemented. It's C code underneath. Okay, so here's what the von Neumann architecture looks like on a microcontroller. The processor talks to the memory, and there's no interposing memory management unit. You know, we've only got physical addresses to work with. There's no memory protection. There's no page level operations or permissions or so on. Things really are very primitive on a microcontroller. We're looking at Cherry, and if you've heard me talk any time in the last 5 years, I will have talked to you at length about Cherry. This is a really nice concept where you've got fat pointers that include validity, bounds metadata, and permissions directly inside the architectural kind of atomic capability data type. And this metadata for pointer access permissions and bounds is checked in the hardware at every memory access. So, you know, you can't kind of circumvent memory safety in a way that you can do in legacy C applications that just have raw pointers. There's prototype hardware available for Cherry, and we've got lots of that at Glasgow. Maybe some of you have too. If not, you can run things in an emulator or an FPGA as well. And the propaganda, that's not the right word, the publicity for Cherry says that it eliminates roughly 70% of critical vulnerabilities, things like use after freeze and buffer overflows and other annoying memory safety violations that cause critical vulnerabilities. Cherry, of course, is not ubiquitous. Microcontrollers definitely are. Tens of billions of microcontrollers are deployed every year. And at the moment, there are several thousand Cherry microcontrollers, memory-safe microcontrollers out there, like this one here. This is a Sonata board from Low Risk. This could be changing soon. There's a startup company called SCI Semi that's taping out Cherry silicon in a RISC-V IBEX core, and soon you'll be able to buy that. But for the time being, we want to get the benefits of Cherry memory safety in legacy language runtimes, because language runtimes like MicroPython really do have vulnerabilities that people are noticing and perhaps exploiting. So we want to try and make MicroPython more memory safe. A big idea then is differential fuzzing. So we're using a MicroPython runtime that's compiled for Cherry and running on a Cherry processor, and an equivalent MicroPython runtime on a non-Cherry system, and we run problematic Python, potentially problematic Python programs on both of them, see whether there's any difference in their runtime behavior, which might indicate memory safety problems. So a key research question is this: can Cherry serve as a practical oracle for interpreter memory safety? So we're going to generate some MicroPython programs that we think might be buggy or cause bugs on the underlying C runtime. We're going to run these programs on our two different runtimes in parallel, the non-Cherry traditional runtime and the Cherry memory safe runtime, compare the outcomes and try and find some problems and use that in some kind of virtuous circle to feedback. Okay, so I'm going to go through these 4 stages in a bit of detail here. There's the 4 stages up the top there. That's like our map here. And the first stage, we've got a few buggy programs. So this is a kind of seed for our corpus. And these come from bug reports, memory safety bug reports on GitHub, perhaps from the CVE database. There's a few MicroPython CVEs published in there. Also from other Python runtimes, we look at those as well and find buggy programs there too. We feed these seed buggy programs into an LLM. Yes, we're drinking the LLM Kool-Aid. We feed them into an LLM and it generates lots more buggy or potentially buggy Python programs for us. And the way it does this is we give it a prompt that says, you know, here is a Python program, generate me some more Python programs like this one. Get some more Python programs, and then we somehow assess these to see whether they're likely to be buggy, and then we use that to evolve the prompt. So this prompt here is evolving that prompt there, and we end up, after going around this loop a few times, with a set of programs that we then feed to a standard mutation fuzzing framework and generate even more programs. So these are what the LLM prompts look like. Here we go, look. Here is a MicroPython function, generate some test cases for it. And then that prompt gets optimized and evolved, and it ends up like this. So you can see this is a more detailed prompt here. And this is what we use to generate our MicroPython test cases. And then we mutate them using the standard kind of fuzzing operators that you'll see if you've done fuzzing for yourself, that somehow evolve, mutate the source code in ways that are going to do interesting things, hopefully. So the second stage then is this dual lane execution, where we run our potentially problematic Python programs on non-Cherry systems like this Raspberry Pi here and see what output we get, and also on Cherry memory safe systems and see what output we get. So MicroPython is running on top of one of these platforms, and we're going to see what the outputs are and capture things like standard out and standard error and maybe stack traces of errors and so on. Yeah, so in the non-Cherry lane, we run on x86 or ARM. We kind of sandbox our code and run it with a 10-second timeout and capture all kinds of dynamic information on what's happening. Do the same in Cherry, which is our memory safe runtime. And here, if we do have memory safety faults, we'll have metadata about those, whether they're out of bounds, whether it is an invalid pointer, whether there were alignment issues and so on. And we'll capture this data too in our Cherry lane. And then we compare the output from the non-Cherry classical execution and the Cherry memory safe execution and see whether we really have got a bug. So if you look at this Venn diagram here, right, these are the bugs from the non-Cherry runtime. Here's the bugs from the Cherry runtime. And where there's an intersection, then maybe that's that's definitely a bug that's triggered in both cases. Where we only see bugs in Cherry, that's a memory safety violation that's exposed by the enforcement of our memory safe runtime. And sometimes we get crashes in the non-Cherry world that we don't see in Cherry. And again, we'll look at these separately and see where they come from. There is a lot of duplication, to be honest, in our crashing programs. Often our mutants are just kind of superficially different. So we might run 2 test cases that expose the same bug. So we have to group these together or deduplicate our bugs and we kind of look at the stack tracers and the return codes and so on, and kind of cluster together crashes that are actually caused by the same underlying problem. And then we'll use delta debugging to minimize the crashing program to try and get a kind of minimum working example of the problem, and feed this back into the LLM again to generate some more MicroPython programs, and possibly use this program to report a bug to the MicroPython maintainers. Great, so that's the process. Very quickly, our evaluation. There's the non-Cherry platforms we ran on, and the Cherry platform was a Morello, which is actually a server class, 64-bit ARM processor, but we're running our embedded microcontroller C code on this platform here for now. We, in a 24-hour period, generated about 8,000 Python programs that were potentially buggy and ran them through these dual lanes. And yeah, the programs cover a range of different areas in the MicroPython runtime. Some things are looking at kind of raw memory buffers, foreign function interfaces, file system libraries, peripheral interactions, garbage collection, and so on. So you see here the 8,000 synthesized Python programs, which we hope are going to trigger bugs in our runtime. And indeed, we do find bugs. So these are the deduplicated problematic cases we found. So we ran, our experiments were really running on MicroPython version 1.20. So this is a few months ago when we ran this code, and we see there are more bugs on Cherry than there are on the non-Cherry system, which is because of the extra memory safety. We couldn't run an FFI on Cherry. We didn't have that working. And then we also looked at a more recent, this is practically the bleeding edge MicroPython here, and the number of bugs was reduced. The number of bugs was reduced, so they have fixed some of them, but there are still some bugs there. Cherry makes finding problems easier. You get precise localization of where the memory safety violation is. A bit like you would in something like Address Sanitizer or Valgrind, but this is much faster and also not random in any sense. These are kind of deterministic failures. And so we see, oops, sorry, my slides are going a bit mad here. We see, for instance, when we try to do array subscripting or memory subscripting, we get a Cherry fault straight away where there's a permissions violation, whereas that fault might not manifest until much later in a non-memory safe runtime where there'd be some kind of data corruption that would manifest itself in an arbitrary way later on. We reported some bugs to upstream MicroPython on GitHub. So here's one of the bug reports that Kai made. And this bug report was monitored and fixed in the open source project, the MicroPython on GitHub. Interestingly, we used an LLM to identify the bug, and Bob, 10,042, used an LLM to fix the bug. But there we go. Yeah, so here's just a few examples of the kinds of programs that we synthesized which caused problems. So can I interpret this Python code in my head? Here's a byte array with some data in it. And then we take the address of the byte array. This is the MicroPython C types interface here. We take the address of this byte array, and then we get a memory view on the byte array. And then we realloc the byte array here. We're kind of growing it and making it bigger, so we reallocate the array. And then we do a garbage collection. And then we use this old view of the original array. We've still got a handle onto that. We're accessing memory that we possibly should no longer have access to. And this is, of course, a use after free, effectively, and a memory safety violation. Here's another one here. This is particularly arcane MicroPython code. And in here, we're redefining the comparator, and then redefining the comparator to clear our array reference and then to do a garbage collection. And then we try to sort the array that we've just deleted. Oops, and we end up with an invalid array during the sort. So this is not very nice code at all, and in fact breaks the rules of Python, which says you shouldn't do things like this in comparators. Okay, so what we see there is that sometimes the code we generate is kind of causing a problem, but actually it's a problem because the API isn't well specified or well understood by the language runtime. Whereas this problem is a real problem and is effectively a bug that needs to be fixed in the MicroPython code. Okay, Cherry is very helpful for debugging. It helps us find our memory faults deterministically and quickly, and makes them much easier to classify because we have this metadata about what the problem is. And indeed, this gives us kind of better precision for using LLM synthesis for creating more test cases of a similar nature. Yeah, in terms of the validity of our experiments, we have noted some threats to validity. Cherry's a nice oracle, memory safety, but it doesn't detect all bugs. So if you have fields within an object, Cherry can't find intra-object memory corruptions. It's only working at the object level. Sometimes if your Cherry system doesn't do runtime tracking of capabilities, then you don't necessarily detect all use after freeze. And it's also the case that it doesn't detect other kinds of errors that aren't related to memory safety. So it's a good oracle, but it won't find all the bugs. Yeah, our seed corpus that we used in the first stage to generate these 8,000 Python programs is drawn from the CV database and other bug databases, but it might not be complete in its coverage of all Python patterns that cause problems. And we've only looked at MicroPython. There are other language runtimes that have been ported to Cherry, including from our friend Tomohiro C Ruby. So that might be another interesting runtime to play with, to look at that in the Cherry memory safe world and in the classical non-memory safe world. Also some WebAssembly runtimes too. So it might be worth looking at those to somehow strengthen the coverage, the broad coverage of this work. Yeah, so let me conclude by saying that this work carefully seeds large language models to generate a corpus of Python programs that is likely to expose memory safety bugs in an interpreter. Cherry is our efficient and effective memory safety oracle, so we use that to manifest the bugs and compare against a classical non-memory safe runtime. And we have identified real-world bugs, some of which we've reported responsibly and have been fixed in open source microcontroller runtime, particularly the MicroPython runtime. Thank you very much for bearing with us with our remote talk, and please do read our paper. And if you've got any questions, Kai and I are here and happy to take them now. Thanks very much, everybody.
So if anyone in the audience shouts out a question, and I'll repeat it to Jeremy because it has to be from here. Do you have questions? Well, let's start. Oh, Steve.
Yeah. In this really constrained environment, I wonder what role formal verification might have, and whether that's part of what is considered.
Okay, so you have a question from Steve Blackburn, which is: this is a very constrained area, MicroPython, very small. Would formal verification be interesting in this space, and what sort of role does it play?
Yeah, definitely. So we've thought about things like model checking, or possibly looking at things like verification of certain properties interpreters in a theorem prover like Lean. Even though MicroPython is quite small, there are still some scalability issues with using these kinds of formal methods. So we're working on it, Steve, but we haven't got any decent results there yet. We'd be happy if you could give us some more pointers.
Thanks, Joe. Cool. Any more questions? No. Nicholas? So you have a question from Nicholas van Kempen. And it's, you're using large language models to generate bugs, but aren't large language models generally trained to not generate bugs? So did you have issues with that?
I think that's a really nice question, thanks. I'm going to invite Kai, who's also on the Discord here, to answer that question. Thanks, Kai.
Sir, do you mean like using LLM to generate bugs and not generate non-bugs? Is there any difference like that?
Sorry, I didn't quite follow. Could you repeat?
Yeah, so I guess we didn't have trouble.
Okay. Cool. I think
buggy code.
Well, my experience is that LLMs do generate bugs. So. I think we're out of time now because I think we're supposed to break for lunch. So thank you very much, Jeremy and Kai.
Thank you. Cheers.
Yeah, thank you.
Sure, it seems it works. Okay. Yep, awesome. Can I get it started? Okay, so, yep. Can you test, Lizzie?
Yeah, I think.
Okay. Yeah, it seems it works.
Am I audible yet? Okay.
Yeah, very good. Yeah, so let's resume ISMM. This is Jung Ho An, who is chairing the third and fourth session. And it's my great honor to introduce Professor Lizzie John. She's a Truchard Foundation Chair in Engineering at UT Austin. Her research interests include workload characterization, performance evaluation, and high-performance architectures for emerging workloads. I want to emphasize that she also conducts research on main memory controllers and allocators. She received many awards, and I don't have time to enumerate all of them. And she is an IEEE, ACM, AAAS, and National Academy of Inventors Fellow. The title and abstract, I just took a look. Reduce, reuse, recycle looks very intriguing to me. Let's welcome Lizzie.
Thank you, Jung Ho. And it's my first time at ISMM. And someone this morning remarked, are you at the wrong conference? Okay, I hope I can speak some things and bring architecture and some of the memory allocation issues together. So at the end, I never felt I was at the wrong conference, but at least one person asked me. Anyway, let me, professors go and talk, but students do the hard work. And I would like to say thanks to my students, and especially Rui Havo, who did memory allocation work. He defended his PhD on allocation and memory management, and he's at Meta now. So probably some of the hard questions, if very specific, may go to him. But I also want to say thanks to the University of Texas that gave me the chance to have colleagues such as Professor John Goodenough. He worked on lithium rechargeable batteries. He received his Nobel Prize in 2019. And also Bob Metcalf, who was my colleague for about 10 years, and he won the 2023 Turing. But let's get to the topic. Memory is a scarce commodity. Probably you heard recently all these sorts of things. The memory companies, the stocks have this is just the last 6 months, how much Micron technology price has increased 5 or 6 times. SanDisk and companies who are making anything using DRAM, or they all have quadrupled or more, 5, 6 times in just 6 months. And there are also all these blogs that you could read about. Even if we had all the money, there is no way to make the memory, like fabrication. Simply fabrication of enough memory is not possible by the world. There are no fabs to make the memory that AI needs. But this is the community who realized long ago that we need to manage memory well. Not now because the stocks are going like that or Wall Street bloggers are blogging. That's not why we were working on memory. This community was working on memory for lots of years and tried to use it well. That has been our goal for lots of years. Now, just coming to the big world beyond maybe computing. Landfills are scarce too. And what's the world doing about it? This is the most common mantra you hear when you think about how to, we need to reduce our consumption, we need to reuse whatever we can, and we need to recycle. Probably this is applicable to memory too. We should reduce whatever memory we are using in our workloads and applications. We should reuse how much ever the same data, maybe use it now rather than use more memory for it. And the locations and the physical memory recycled, we have been doing these things. But we probably may need to pay a little bit more attention. On one hand, we can try to fabricate more memories, but AI has made the need so much that may not quite, it may be hard to catch up. And there is so much importance for reusing and recycling. So go to the first one of those, reduce. What are we doing in AI nowadays to reduce the memory we use? We talk about quantization. Instead of the 32-bit data, maybe we use 16 or 8 or 4, or even maybe binary neural networks with 1. So you can reduce. We have some effort. It's not every application, but there is an effort in that. We do pruning. And that reduces what we are doing maybe, but some reduction. Mixture of expert models. So we do not use all the coefficients at the same time. We only use what we need, or bring just the expert, some experts. That's reduction. So there are some things happening in AI to reduce how much memory we would be using. But look at the growth of our models. While it's true we give some effort or put some effort into reducing how much memory we are using, the models are just growing as we speak. Every day, every week, new models and lots of growth. It's not just that the amount of memory needed is growing, is becoming 4 times or 5 times the previous model. The bigger fact is, what is the relationship of the memory that's needed to how much memory you can have in the system? That, the orange line, is basically, this is a little bit dated, but 23, and the trends are the same. Trends haven't changed. So the orange curve is what GPUs have. And that's only growing so much. The green is how the models are growing. And that's the gap between the two. Up to 22, we could still afford to fit a lot of models. But since 22, the gap between how much the models need and how much memory exists in a GPU, that has widened. And you cannot fit models in GPUs. So that makes it worse. If it was, okay, it became 5 times, 10 times, 100 times, but I can still fit, that was a different story. I cannot fit. That makes this issue extremely challenging, and it's very important. We need to deal with this. But thinking, looking at this, AI, reduce, probably that's not happening, because coexisting models, even if you do some quantization, some pruning, but the number of models you are using, the number of models that need to be coexist, everything is in models themselves increasing. So AI, most likely, the reduce is not going to happen looking globally at AI. It's not going to reduce the amount of memory that you need, because we love capability that AI has brought to us. The world loves that capability, and capability that wins over efficiency. So hardware, maybe we can talk about, I want to be efficient, I want to use the least amount of memory, but are my models capable, and is it the highest capability? So we probably will not reduce the amount of memory that we need, that we will use in AI significantly, no matter what all we are doing. But we should, there is no reason not to do it. And it'll just, if we keep saying, we should reduce the models, quantize them more, we'll just sound like the grandpa or the monk who says, last person to leave the room, please switch off the lights. It's just going to be boring advice, and the world is going to use more memory. Now let's come to the second one, reuse. So what is reuse traditionally in computer systems? Locality of reuse, caches have used that. In order to increase the amount of reuse, the same data used again, we do tiling and blocking, and we algorithmically increase the reuse historically. We have done many things in many computer workloads. But locality and parallelism often conflict. So the last decade, and with AI workloads, last decade or two, we have been moving in the direction of more parallelism. And when you have a lot of threads running, they all need some tensor. If we keep one copy of the tensor and every thread has to access that, things are not going to go to parallel. So we copy a lot of data. We duplicate a lot of data. And so with the emphasis on parallelism, which is necessary to do the computation in parallel, the reuse of even things coefficients that are needed multiple times, but we are probably keeping them in separate locations for each thread or each, So reusing more is not likely to happen. Parallelism wins over locality. Locality has been one of the favorite principles of computer architects. Professor Harvey Cragen, who was my colleague, he used to say there are only two principles in computer architecture. One is locality, and the other is pipelining. Everything else can be created by some combination of this. That's it. But this parallelism right now is going to win over locality, and most likely reusing more. Many algorithms are going to distribute data, and they are going to duplicate data so that you can compute more and you can use the computation resources more. So now we come to the third one, recycle. I am meaning by recycle in this context, we have some locations. We want to use that same memory location for another piece of data, and so the location is the use of it is being recycled, that context. And traditionally, caches, virtual memory, the replacement policies would handle this, and historically these things that used to work well. And we collect garbage in the best way so that same locations could be used again, free locations. But with GPU and CPU and the movement of data in between, there is a lot of shuttling of data happening, because models are large, things are not fitting. CPUs have more DRAM. GPUs have less high bandwidth memory. So when things are not fitting, there is movement of data between them, and the scale of shuttling is only increasing. So it is true, we are trying to use that location because there is no other location to use, but it leads to a lot of shuttling, and you have to, if you don't do it efficiently, you wouldn't benefit in performance because you are communicating way too much. Even in a simple GPU cluster, this is just 2 nodes, and the CPU, 4 GPU, each node has the 2 CPUs and the 4 GPU. There is NVLink, higher bandwidth. There is PCIe interconnect. There is NVMe and flash memory. So there is SRAM, there is DRAM, there is high bandwidth HBM, there is flash. This exists even in small memories. And each of those channels have different bandwidth properties. Each of the different types of memories have different capacities and different speeds. So previously, when we were managing the memory hierarchy, we were looking at, a little bit of cache, maybe L2 and L3, complicated things a little bit, but still the channels were more predictable. We knew what is coming from what can come from DRAM to the last level cache, what is the speed, what is the bandwidth. Now it's a variety of channels. And the variety of channels include, give you more possibilities, but it also makes life difficult, because if you do, if you make a mistake in your judgment as to where to put this data and which path to use to move it, you could be doing really poorly. So, and how to do that, it is complicated. So this favorite picture of us, our community, with the locality and large amounts of slow memory at the bottom and small amounts of fast memory at the top, and all the cache, the cache policies and the virtual memory policies would bring the right data to the top, and you have it at the top. It worked when programs had a lot of locality. Now that with the amount of parallelism we are exploiting, the locality that in effect you can get has reduced, and this basically, it doesn't seem to work anymore. And the complications in moving data across the hierarchy has increased and is increasing more, because we want to use large amounts of NVM, non-volatile memory. Because the volatile, if it is non-volatile, you don't lose the data, you don't bring it when you start the system. Non-volatile memory. So there are different kinds of memory that is becoming feasible to use, and they all have different properties in terms of their capacity, their speeds, the bandwidth they offer. Now we have to kind of do linear programming between all these options in the fine phases of the program that we are executing in order to do well. It's not simple, it is becoming complicated. And the future is going to be even more complicated, because what's coming is the chiplet era. And chiplets, so you will have already in GPUs, we have the GPU chiplets and the memory chiplets and multiple memory blocks, and so they cannot be treated the same, because they are located different amounts of distance from the core that's computing. So even if the memories in this picture, actually I have the memories shown with different colors, but for a moment, let's simplify the left side picture. So the green things in the middle are the processing computing cores, and the sides, let's assume they are all the same in terms of capacity and bandwidth. But your distance from the core that needs the data, how do you place the data? How do you partition the data among the different memory pieces? And how far are you from whichever core needs that data? It's not a very easy problem to solve. And now on top of it, you assume that they are not all uniform, the same type of memory. Some are HBM, some are DRAM, some are PCM, or different types of memory. So the memory technologies are coming up with many more memories, and many memories which previously used to be simply experimental are reaching the stage of you can use them in a system. So when you can use these heterogeneous types of memories, even if you were only doing 2.5D integration, the 2.5D just means that the left side, which means there are the different chiplets sitting side by side, and there are connections between them can be routed in a little layer underneath them. And so the interposer layer helps to connect these pieces. But now there is even more variability in the speed of memory because of the distance. And then come to the right side where 3D integration is possible. Chiplets can be on top of each other. What are you going to put on top of the GPU? You put some HBM, you put DRAM, do you put flash? How many things? Are you going to put it uniformly on every GPU, or some GPUs will have more flash, or nobody knows. But this is the time Even architects have this opportunity to come up with systems, but unless software uses the system correctly, it's not going to work. And managing the memory, even in that heterogeneous environment, is going to be extremely important if we are to deliver efficiency for future workloads. Lots of 3D integration possibilities. Packaging of semiconductor chips was not something I was interested in for 25 or more years of my career. But the last 2 years, I am paying attention to it, because for the first time, packaging opportunities are giving me the chance to architect different types of systems and memory, and how much I can communicate the bandwidth offered by the memory, what types of memory do I want to integrate, and what does it offer me in terms of a better memory system. So there are more opportunities coming, but so with these 3D memories, basically you have this layer in between where you could be communicating a lot more. Much higher bandwidth is possible because the chips are close to each other. Also, if you look on the top right picture, packaging experts, and I'm not an expert, I just listen to them to understand what are my opportunities. Chips can be put, they call it back end of the line or front end of the line. You can put chips the same way, stack them up, or the opposite way, so you could, thermal management, different problems, but lots of opportunities to put chips in different ways compared to what we were able to do in the past. But all of those opportunities may help us to have more memory in the system, but it will also complicate the memory management. So why is this? Probably you know it. I shouldn't be talking to this community on why memory allocation and management are so complex. Coming from the application or framework, and with all the AI, CUDA, runtimes, kernel drivers, unified virtual memory management, the UVM, and then the hardware, the different types of memory, and then the CPU and the GPU shuttling the data between them. So many pieces in this picture, making it complicated. And allocating a large chunk of memory and managing fragmentation, balancing allocation speed and fragmentation, everything is complicated. And it was complicated enough on CPUs, and we try to optimize a lot. And optimization is the root of many evils. We are spending time figuring out what's the best thing to do, best way to do. So it keeps complicating the metadata, complicating the management of the metadata. So there is a lot going on there. And with multi-threaded applications, of course, the complexity increases. And either the metadata can grow, or the synchronization problems happen. And so cross-core metadata exchange, you have been working on techniques to reduce the problems with the multi-threaded allocators, but it's complicated, and this community has contributed a lot to that area. And lots of papers, the very famous Horde paper, and Catherine McKinley is my colleague for a bunch of years and friend. And we had Emery's paper this morning too. So a lot of things going on. Lot of allocators, and industry and academic works on them. If you look, activity, daily updates on how to allocate things better. And processor performance is highly sensitive to memory allocation, even with this. And this is CPU with 3 different allocators, JE-malloc, TC-malloc, and me-malloc. BFS, performance, this is the variability. And then another benchmark, Larson, And it's not the same in different programs, the variability. So different allocators optimize performance in different ways. There is no, it works for everything, one for all solution. And the complex metadata in the multi-threaded allocators lead to cache pollution and synchronization overheads. So we did some work on that. And if you increase the number of threads, the cache misses from the metadata side. So this is the darker section at the bottom of each bar is the cache misses coming from the metadata, and the other one is coming from the true data. So the metadata cache misses keep increasing when you have more threads. Similarly, the synchronization cycles as a part of overall cycles keep increasing when you have more threads. Naturally, we can understand because we are doing the metadata management, there is stuff to synchronize between the threads and it happens. So the metadata in these multi-threaded allocators leads to these sorts of problems. Now on top of all of those, the CPU to GPU communication is going to bring in another angle, another dimension to the complexity here. And the CPU-GPU data transfer and the management. When NVIDIA and the GPUs came by, first we allocate everything on the CPU side, CUDA malloc, and then you do a copy of the data to the GPU. That was how we started. There has been a lot of improvement, progress, more work, lots of work on how to make this problem better, or this problem solved. So the user space, there is the memory allocation in the CPU side. To the GPU, how you move it and how you control that transfer, there are a few different ways to do it. You can pin certain things to the physical memory in the GPU. You could do asynchronous copy. When you are computing, you could still be moving stuff ahead of compute and so on. The dream is to have a virtual memory, one address space. Whatever we were enjoying on the CPU side, can we have it with CPU and GPU together? That's the dream. That's the programmer's dream. I don't have to deal with this. I just think of it as one. But the GPU has the high bandwidth memory, but less capacity. CPU has the DRAM and a lot more capacity. So we still have to deal with these transfer issues. And so CPUs were complex enough, but now with the CPU-GPU transfer, this issue has become even more complicated. So, and the CPU-GPU data transfer, the UVM, you could do on-demand data transfer at page granularity. Just, you don't do anything special. We just want to treat, the unified virtual memory. Or you have the pinned memory, and you can, the U1 line shows, whatever kernel you are running, you are moving the data for that into the physical memory. Or you can have asynchronous memory copy. The red lines are actually the same as the U2. The red lines are zoomed out representation of moving things from the GPU DRAM to the SMs or the compute threads of the GPU. So the shared memory inside each thread is going to get data through that asynchronous mem copy. And you would, without the pin memory or UVM, you would write code in whatever way. So you have more code to write. With UVM, it is simple. So UVM would be nice if it worked, if it gave the same performance as the other cases. But when you look, UVM doesn't give the performance. So at this point, UVM is more for convenience. It's not for performance. UVM is for convenience. The programmer productivity can be higher because it's convenient, but you do not get the same performance as async mem transfer or the pin memory. You could do better with those techniques, but it's more inconvenient and you need to think what you want to do and so on. So more than 4x performance deterioration when you go to the UVM, which is convenient. And these were some small benchmarks. We worked on this some time back, but recently we did some LLMs. And of course, what did virtual memory offer you one time? We could fit in applications that wouldn't fit in our memory. They would come as you need, and you didn't have to know anything about it. So if you take LLMs and you oversubscribe them, so the system doesn't have enough memory to fit everything, and the green bar, there is no oversubscription. The model can fit. The orange bar, there is like 2x, 2.5, 4x oversubscription. And the red bar, almost 5x oversubscription. So the UVM is going to manage the movement of data, and that's nice, that's convenient, but you lose a lot of performance. It's not even the 4x on the previous page. The 4x on the previous page was for tiny micro benchmark. For these, it is 1000x, something like that, huge. So it's convenient, but practically we cannot use it. Because if things are going to be this bad, that's not good. So we need to figure out a way to manage this data movement in a way that, it still is feasible to use it performance-wise as well. So this is not, if you work on it, you can make it better. And so I have a student who is doing some work on it, and this is not published data yet, but preliminary data, we can reduce it by half or something. But that's not, what you are looking at here is not something, it's huge. So, but you can reduce it by about half by prefetching some models early in parallel. You have to carefully juggle this. That's what you have to do. And a lot of the data movement or memory management challenges are introduced by the KV cache in LLMs. In KV cache, there are the query token and then the key token. Q has to be multiplied by the key, and then the QK is multiplied with the value token to get the attention, and you continue this process. So the KV cache keeps growing, the QK keeps growing, and when you have to, as the batch size or the sequence length increases, the cache size that you need becomes large. You do not have space to keep it in your in the GPU's high bandwidth memory. What can you do at that time? You offload some of it to the CPU's DRAM. But then you have to bring it back because you need it. So you have to keep shuttling. But offloading KV cache is a technique that researchers have come up with in the last 3 or 4 years. A lot of work has happened in things related to this. So Paged Attention was a paper where the KV cache offloading, and then there is VLLM, there is Pi, there is a lot of work about how to do this KV cache offloading. So let us say this was, let's say we have a system with about 40 GB HBM, different runs depending on the batch size and depending on things. It may be sequence length, it will grow. Can I let the KV cache take as much space, or when do I decide? So you put a cap on, okay, let's say I will give 26 GB for the parameters, 12 for the KV cache, there is intermediate data and other things going on, and 5% for the other stuff. Just think. If you, with a higher request rate or a larger batch size, KV cache may run out. And when KV cache run out, you can see when the request rate increases, percent of available KV cache is reducing, there is no more space to put anything, and the token latency is going to increase. And so the latency is 2.5 times higher when I increase the request rate just 3 times. So we do need to manage this well in order to get a reasonable token latency, reasonable performance, and space is limited. That's all we have to use. So VLLM, if you don't cache it, you have to recompute it. So do you want to recompute the KV, or do you want to cache it and bring it back? So it becomes this trade-off in save it, bring it back, or recompute. So when to trigger each of those operations, there are some heuristics different systems use to decide when will I push it out, when will I decide forget it, I'll recompute. And so we have some work. This is in SOCC last year. And this is, so the major works that had come up at this time to deal with this problem, they were all offloading KV cache. Offload KV cache, bring it back when you need it. So CPU DRAM has the parameters. You bring the parameters to the GPU HBM in the beginning, then computation starts, KV cache is created, KV cache doesn't fit, you swap KV cache into the CPU DRAM, and CPU DRAM has more space. You can grow the KV cache, partly in here, but the rest in there, but you have to bring it back as you need it. And you could transfer a layer in parallel to the compute to get better performance. You could reduce the latency up to 2x by doing things like that. That is what some of the papers show. And an alternative is, let's just remap the parameter, because even all the parameters are not used all the time. Different layers, you are computing certain layers. So you don't need to bring all the parameters to the GPU. Instead, you could be shuttling the parameters as opposed to the KV cache. You may ask, how does it matter? It matters because KV cache is dynamic and it changes, and you have to put it and bring it back. Parameters are resident in the CPU DRAM. It's not changing. So you just have to invalidate them here, and you just have to bring it one way, not two ways. KV cache, bidirectional traffic. Parameters, only one direction. Whenever you need it again, you just bring it back again. So that is what we did in this. Parameter remapping is unidirectional, and it's not dynamic data. That is what the model has. So there isn't as much overhead in synchronizing or bringing it both ways as in the KV cache case. And now several models coexist. Agentic AI, multiple agents working, when to trigger the remapping, which models to remap, how many layers to remap, which layers, so there are more decisions. Management becomes even more complicated, okay? So dynamically remapping the parameters, not the KV cache, to elastically resize the KV cache. That is what is done in this on a SOCC paper last year. And essentially, there is the metadata, there is the remapping controller, and the transfer engine. And we select, the scheduler will select which models to serve, because multiple models coexist. And inferences, you want to give the quality of service. You also want to get the lowest energy, best performance, lots of things, right? So scheduler does its job. Memory allocator updates the usage parameter and KV cache. And remapping controller determines whether to remap the parameters. Async transfer engine does the GPU-CPU transfer, and the GPU executes the LLM task. So this is what was done in this. And essentially what we did is, if you have so many layers, the kind of halfway away from you, that's the parameter we will send to the CPU. And when you send it to the CPU, hopefully we have enough time before we need that. We could bring it at certain time ahead of when you need it. So, so the running layers and the remap layers, the remapping controller manages it, and the details are in the paper. Probably in the interest of time, I'll just go through. So you don't want to be remapping the layer closest, or if you just use that and you know there is a lot of time to get there again, we could offload that. Offload doesn't mean you're moving it, you just invalidate it here, so we will bring it back later. That's all it will do. And on arrows, for time between tokens, time to first token, and throughput, it could beat VLLM and Pi, which are the prominent other methods to have, which did KV cache offloading. And details are in the paper. And we also saw that it is better to cap the number of layers you would remap. You don't just let you remap or send the layers out. When you, with a larger request rate, if you don't cap it, things may be bad. So you also have to cap how much you may ever remap. So lots of variables to engineer, and but if you can do a good job, you can get good performance, higher request rates, and better throughput, and so on. Microsoft's deep speed with this and Flash NVM and the NVM Express protocol. And this one was for training. This work was like 2 years ago. And lots of opportunities there as to what to offload and what to put where. The model state can be partitioned, and you can offload different things into the NVM. And deep speed allows many options. They call it 0, 1, 0, 2, 0, 3, 0, infinity. There are a few different choices. And you could offload different things. And on that system, I showed the small GPU cluster with the 2 nodes. We no, actually, this was not on this system. It is on a bigger system. And, oh, I'm sorry. It is on this system with the 2 nodes versus the 1 node. And you could actually see we could fit in bigger models on 1 node as opposed to more nodes. So in here, it is just on the single node. If you didn't do deep speed, the size you can fit is a lot smaller. With deep speed, you can fit larger models on 1 node and on 2 nodes. You could do that. But the more interesting thing is perhaps this one, the top picture, the achieved model size on a single node. The last blue bar shows what is the size of the model on the single node, and it is bigger than the one on the dual node if you offload into the NVM. When you have 2 nodes and you offload into the, so the 1 node, it's easier to offload to the NVM and get the benefit. You can fit the larger model. The second and the third set of bars show that your throughput is less, memory usage is more. So there are all the downsides, but simply the model fits, which is valuable for a lot of customers who do not have 2 nodes. They only have 1. And they would rather fit their model on that 1 node machine rather than have more GPUs. So there are different ways to optimize. Sometimes it is, yeah, it's possible, that's it. It's slow, it takes more memory, but it's possible. And other times it is, we just want better latency and better throughput. So you optimize and manage the movement in different ways. So with deep speed, the single node could achieve a higher model size than the dual node. And more details on that in this ISPAS paper from 2024. Recent, a lot of discussion on workload-specific management. It makes me a little bit sad. We used to be able to manage workloads automatically. Now all of a sudden we are like, we can't do that, it's not working, we need to manage more workload-specific. Maybe we will still, so this isn't working, but hopefully we can make it to work soon. We will figure out heuristics and processes to make it to work. And even when the 3D chips will come, we will still do it. But basically, temporally or spatially, we need to pay a price when we have the large models. There is no way to escape. Somewhere you have to pay the price. With the types of memories and the different bandwidth and latency considerations for each piece, CXL, which has been a big thing in the architecture world in terms of expanding memories, architectural innovations like PIMS. I guess last year there was the keynote on the PIMS. But PIMS, again, a big locality problem. This paper, this is Proteus, one of the PIM papers. If you look, it works for many workloads. Wherever matrix multiplication is there, it doesn't work. The things I have highlighted are when there is matrix multiplication, the first bar is GPU, and then there are PIMS, and PIMS, the performance is poorer compared to GPU because the locality, the matrix multiplication, the reuse is very high, and in PIMS you have to copy all the data or you have to keep shuttling data to where the compute is going to happen. So it's challenging. It's not very easy, and algorithmic innovations are needed to handle this problem. Different types of neural networks. In another part of my life, I do weightless neural networks, no coefficients. It's lookup tables, RAM neurons. It has fascinated me very much that I'm working on those. And co-designs. People like this conference, I guess between the morning and the afternoon, we are trying to actually learn from each other, and we need to do more of that. Because no one branch of science can solve this problem. This is, we need to work together on it. Different kinds of computing. So, and on the, again, when it comes to FPGAs and hardware accelerators, another set of optimizations. We need to work on all of them. So, I would like to end with a note saying, there is memory management, there is something in it for everybody. Whether you like hardware or software, there is something in it for you. You are somewhere there, okay? And all these layers are important in getting this done. Whether you like algorithms or architecture, you have something in it to do. Plenty of opportunities for all to improve how things are happening. But, reduce, reuse, recycle, we need to think about this, work on it. But recycling the locations or the memory management, a big part of it. And I will end there. So thank you for listening, and I can take some questions.
So great talk. I think you actually set excellent stage for the following sessions. So the all two papers coming related to what you said. Before moving on, if there's any question, yep, please, hands up. Anyone have any question? If no, then let me ask one question first. So in the middle, you mentioned about the unified virtual memory, but for example, Grace Hopper or kind of follow-up, which on Rubin, those systems have some unified CPU and GPU memory shared. Do you think that is really needed, or the kind of conventional separate memory space between host memory and device memory suffices for AI or LLM inference?
I think it's a good idea to have them. It's not working now. It's working poorly. But human productivity is a big part of all this. Humans are the most valuable commodity right now. Okay? So humans are a big resource, and creating applications will get speeded up, bugs will be fewer maybe. And so it is a nice thing, but it's not working now in terms of performance, and so it looks like a bad idea at this point. But only if a lot of people work on it, we can turn the bad idea into a good idea. But I would say, in spite of the poor performance, we should do it. That's my personal opinion. Just in the long run, at some point we will reap the benefits, if not now.
Hi, very interesting, Nadav Amit, Technion. I wonder, in memory pooling area, which is different, many times people talk about overcommit ratios of not as high as you show here. And even in those cases where memory footprint is more known and we can do all kind of optimization, it fails many times. Like memory overcommitment ratio of 2 is not something that works well with memory pooling. So why would it be any different in this domain if we fail with much simpler access patterns?
I am not completely sure I understand the complications in the pooling versus this, but I would say, I think the biggest challenge as I see it is the capacity requirement for multi-tenant models is so high. It's not 2x, it's not 4x, it's way beyond that, that we have to work. It's not 1.1x, and it is not, it's not that small. And the way AI is used by the world, I don't think there is a way it will come down. It will only go up. So I think there is a difference in how much oversubscription is needed just because of that.
The fact you need something doesn't mean you can do it. So that's the only thing I'm trying to emphasize.
The only, so it's complicated, and the need is very high, the way the world wants things to work. Otherwise, we just have to say it is, it will be slower, it will be like that. But if, we should, I think, we have to figure out a way to automatically move the right data to the right compute at the right time, right? So, and allowing oversubscription as large as 10 or even 100, why would it not be possible? Because if locality was there, it would have been possible. For reasons I mentioned, it's not looking possible at this time, but maybe there are ways. If we keep working, we'll come upon something. That's my feel. I'm optimistic always.
Okay, I just have experience with NUMA. Thank you.
Yeah.
Great. Any other question? So then let's thank the speaker. Oh, sorry.
Steve.
One thing I picked up from your talk was, or tell me if I'm wrong, but growing heterogeneity in the what's available compared to, say, 20 years ago, and what that means for people developing software. Here I'm trying to draw a bridge between the two, the morning and the afternoon. And I just wanted to know what your thoughts might be about that. First of all, did I read it properly that you foresee growing heterogeneity in what's available? And then the next part of my question is, do you have thoughts about what this means for the software community, in the sense that presumably if that's true, then it means optimizing for a much more diverse set of platforms, if that makes sense?
Yeah, I think heterogeneity will grow because capacity, price, considerations for some new emerging memories are very attractive to be used in systems. And so far we were living with volatile memories, DRAM and anything above that. And non-volatile memories are useful. We can design systems in different ways when we have non-volatile memory. So it will only become better. My colleagues in the semiconductor area, they are talking about lots of fancy memories, which they are saying is close to being actually fabricated and really made production. They have experimental small pieces, but they think it's coming. So in 10 years, 15 years, that sort of range, I believe it will be heterogeneous. Now, what should software developers, should you go learn all these different types of memories and then try how to program? That's why I argued for the UVM. Okay? It doesn't make sense for software developers to have to understand all the intricacies of all these heterogeneous memory. That is why we should develop something that will work like the virtual memory that we used to have. So the UVM, in spite of bad performance now, I really think we should work on it just for that sort of reason. Yeah, we should free programmers from this. And so we should come up with ways to free them so their productivity is high and bugs are fewer. Yeah.
Okay, with that, let's thank the speaker again.
Thank you.
So we'll move on to the next session without any break. And Yoon-ki, please come. Please.
Yeah.
Mike. So next session will be quite short with 2 papers, but it's all about the GPU, especially regarding how to understand the unified memory. The first one will be given by Yoon-ki Shen from Virginia Tech. I think he is about to be ready. The next talk is about the consistency and coherency, how to understand that on the unified memory processor. That's the NVIDIA Grace Hopper superchip stuff. And this is the work done by the collaboration on University of Utah, Duke University, University of California, Santa Cruz, and I think Soham Bakshi will present, and his advisor is there as well. So, yep, where? Yep, I think it's ready. So let's welcome the speaker. Oops. Take your time.
Check. Sorry, apologies. All right, good afternoon, everyone. Thank you for attending this talk. I'm Soham Bakshi, and this is titled The Consistency and Coherence of the NVIDIA Grace Hopper Superchip. So from Dr. John's keynote, we learned about the problem of memory shuttling in these shared processing unit spaces. And in the previous talk, we saw what strategies developers can use to actually kind of mitigate that shuttling problem. But don't you love it when big companies listen to our problems when they develop new hardware? That is what the NVIDIA Grace Hopper tries to achieve. It boasts a hardware cache coherent layer, which not only allows you to use the standard malloc allocator for your programs, but you no longer have to worry about mem copies. There are no page granular migrations whenever you touch anything. But don't you also hate it when vendors don't tell you exactly what is going on under the hood for these new technologies that they release? And that brings us to the two main questions that our work poses, which is what is this? What is the model? What are the guarantees of the rules? What are the rules governing shared memory programs that are written and execute on this hardware? As well as the how, which is how is the hardware actually implementing these rules, and what interactions, what movements take place within this cache coherent layer that allows us to write and run these shared memory programs. Now, there is some amount of folklore and speculation about what actually happens and what's supposed to happen, but largely this has never been validated. It is folklore. And our work changes that. We validate and demystify what goes on within this Grace Hopper superchip. We run 1,960 heterogeneous litmus tests and validate the ARM PTX compound memory consistency model, which allows for CPU side code to compile independently, GPU side code to compile independently, and in the shared playing field, they compose well together. We also discovered read, modify, write operations that are stronger than this compound specification dictates. And we'll get to that later. And we also probe the coherence protocol with which this shared system works using a new method called value propagation tests. With this, we discovered that the Grace CPU has a classic single writer, multiple reader type of coherence protocol using writer-initiated invalidations. The Hopper GPU uses write-through L1 caches which self-invalidate on an acquire operation. And finally, we saw that this NVLink C2C interconnect that is providing this cache coherent layer, that is providing this 900 gigabytes per second bandwidth, that actually uses an Amba Chai-like protocol to bridge the gap between this SWMR CPU and the Hopper GPU. But what does this mean to you as a developer? You have written a new program which has C++ code on the host side and CUDA code on the device side. And some part of this complex program has this simple synchronization pattern for data sharing. We write the data and we release a flag, we set a flag. The consumer, which polls on the flag or reads the flag, once it acquires the flag, it knows that it can successfully read the data. And then you call the NVIDIA compiler on your new $1 million app, and that in turn splits your code into its host side counterpart, which is C++, and the device side counterpart in CUDA, and calls the individual compilers in the backend, so GCC or Clang for the CPU, and the CICC or PTX compilers for the GPU. And they produce these assembly instructions. We have two stores. We're representing data and flag using X and Y, and we will do that for the rest of the talk for brevity. And the $1 million question for your $1 million application is, are these guarantees enforced? If I read a Y value or a flag value of 1, am I guaranteed to read the updated 1 value of X? Now, the rules governing this is known as the consistency model. And ARM CPUs and the ARM v9 ISA, it specifies a variant of relaxed memory consistency known as release consistency, where for these operations, all bets are off. The store operations can be reordered, the load operations can be reordered, and this value of X equals 0, this is permitted by the model. Now, that doesn't always work well with the program you're trying to write. So as a developer, you can annotate your operations using release or acquire or even fences. These operations are synchronizing operations, and they enforce these orders. All prior operations will happen before the release. All future operations will happen after the acquire. You can annotate the stores and loads as these, or you can also use fences that have the same keywords to do the same kind of ordering guarantees. Now, GPUs have used the PTX memory model, and that is also essentially release consistency. But on top of that, it adds this notion of scopes. Scopes are boundaries that kind of govern where this synchronization is valid and permitted. So we have the narrowest scope, which is the CTA scope. And if you use CTA scoped operations, then your release and acquire will synchronize as long as both of those producer and consumer threads are in the same streaming multiprocessor. And they use the L1 cache in the SM for that synchronization. A wider scope of the GPU encompasses the entire GPU as a whole, just the single GPU. So any two threads anywhere on the GPU, any SM, will use the L2 cache to synchronize. Again, you still do need those release and acquire operations. They'll just be annotated with these scopes. Finally, we have the system scope, which in the case of the Grace Hopper includes all of the CPU threads. And in some network NVLink configurations, it can also include other GPUs on separate devices. And this one, we believe, will use the interconnect as the site for synchronization. So when the two threads and the two synchronizing operations have compatible scopes that subsume each other, it is the PTX memory model defines it as morally strong. These operations are morally strong. Therefore, you will not see any weak behaviors. You are not allowed to read that stale value of X equals 0. So if your threads are within that scope using release and acquire, we're morally strong. Your program works as expected. So the main work, the focus of our work was to evaluate this shared memory paradigm. But before we do that, we have to establish our baselines with the individual memory models themselves for the CPU and the GPU. So we use the Litmus 7 suite to test the Grace CPU's model. We run 10 variants of the message passing litmus test. And that store, load pattern, it is message passing, and it is a prevalent design for a lot of multi-device data sharing applications. On the Hopper GPU, we utilize the parallel thread execution environment by prior work from our team. And here we extend these 10 message passing variants to include all of these scope combinations, and we get a total number of 560 just GPU litmus tests. And we test asymmetric cases where we have a release but no acquire. We combine release operations with fences, vice versa. And essentially, we're all good to go. The Grace CPU accurately enforces the ARM v9 model. The Hopper GPU enforces the PTX model. And this essentially indicates that if your program is using the correct pair of synchronization operations, then the weak outcomes are forbidden. For the GPU, it's the same case, but with the added nuance of the scopes. So now that we have established this, we can finally ask the question, what about this ARM plus PTX CPU GPU situation? So prior work posed the concept of compound memory consistency models. And this has two main components. One is that each device retains its own native model. So your CPU code will conform to the ARM model, GPU code conforms to PTX, and they can compile independently using your existing compilers. But in programs where they are required to interact, these models will compose with each other. And for the case of the Grace Hopper, unscoped CPU operations would be upgraded to default system scoped operations. And that way, you can imagine a sense of morally strong in the CPU-GPU system as a whole. And while this was posed as like a potential concept, it has been assumed by developers who are writing these shared memory programs, but it has never check. So this is where we are. We have this notion of compound models, which makes sense, but it hasn't been validated, which developers use, but we don't actually know if the hardware follows that or obeys those rules. And just to, again, remind everyone, we're no longer in that page migration-based unified memory. Here, the CPU can access GPU memory, low latency, GPU can access CPU memory, and it is hardware cache coherent. So this is what we wanted to validate. And to do that, we go back to our message passing litmus test, and we vary it with different store operations, different load operations. We vary the scopes for the GPU operations, and we also try fences. And it goes without saying that we tried patterns where we have CPU producers paired with GPU consumers, as well as vice versa. And these four combinations, combinations along these four parameters, yielded a total of 1,960 different variants of just the heterogeneous message passing litmus test. So what does this look like? We saw this exact pattern before for your $1 million app, where the store to X is followed by a release store to Y, and the Y is our flag variable. The PTX consumer has a load acquire at the system scope, followed by a load of X. And we know from this compound model that the store release on the ARM producer is system scoped by default. And given that the PTX consumer is also system scoped for the acquire, this is a morally strong pair. The scopes subsume each other. We have the necessary synchronizing operations. We are guaranteed to read the value of 1 for X. But consider this variant, where the only thing we change is that we downgrade the PTX load acquire from system scope to GPU scope. And if you remember the diagram earlier, GPU scope only includes all of the threads on the GPU, and it does not include these CPU threads. This is not morally strong. And the synchronization, even though we have the strong synchronizing operations, because the scopes don't subsume each other, we don't have the guarantees of reading. We don't have any guarantees, and we are totally allowed to read this old stale value of x equals 0. It's not the case that we will always read this value of 0, but the hardware is allowed to reorder and optimize, and you may see these. And in our tests, we did see these cases popping up. The other pattern is where, with this example, we looked at how the scopes are important for synchronization. In this, we have the same message passing litmus test with a PTX producer instead. And instead of using store release and load acquire operations, we're using fences, which do the same thing. In this example, again, we have a release fence with system scope on PTX. The ARM DMB barrier upgrades to system scope by default. This is morally strong. We are guaranteed to always read the value of x equals 1. But consider this variant where we simply omit the barrier from the ARM side. Now, the synchronization operations are no longer what they're required to be. And even though the scopes include each other, we are missing this other aspect of correctness, of memory consistency guarantees. And because of these insufficient synchronization operations, the memory model no longer guarantees that we will see the updated value of x equals 1, even if we see the correct value of y equals 1. So both of these are actually in line with the compound model. The ARM operations will proceed as they do. The PTX operations proceed as they do. And as long as the scopes are system scopes subsuming each other and we have the correct pair of operations, our shared programs will work the way we expect them to. But omit any of these and all is fair. Now that we know what to expect as a developer, we also want to know a little more about how the hardware is allowing these to happen. So the next thing we do is we probe the coherence protocol implemented by this system. Now, for those of you familiar with coherence protocols, would know about largely the two categories of coherence protocols that exist. The first is single writer, multiple reader, using writer-initiated invalidations. This is commonly implemented by protocols like Moesi. And how it works is, like, for example, in this case, we have 4 CPU cores with L1 caches. They all load the value of x. The MR and SWMR is multiple readers, so they're all allowed to read the value. They all cache this initial value of x equals 0 in their L1 caches. All is good. Now, at some future point of time, core 3 decides to update the value to 1. And when this happens, it immediately sends out invalidation messages to cores 1, 2, and 4, which all have this stale x equals 0 value. So at this point, the next time C1, C2, or C4 want to read x, they will miss in their L1 caches, and they're forced to retrieve the updated value from the LLC. Contrast this with the other style of coherence protocols, which are speculated to be what GPUs use, which is write propagation with explicit synchronization. And here again, multiple readers are permitted. So we have 4 SMs. They all read the value of x. They all cache it in their L1s. Now, at some point in the future, SM3 updates the value. But what happens now is that no invalidations are sent out. SMs 1, 2, and 4 still have the stale cached values of x equals 0 in their L1s, and they will continue to read this same value again and again, even though the value has updated elsewhere. They are completely oblivious to this fact. Sometime later, SM3 will use a release operation, a synchronizing operation, and that will write back this updated x equals 1 value to the LLC. And even at this point, the other SMs are oblivious to this updated value. Only when one of the SMs use an acquire operation will they invalidate their own cache, And at that point, they will also, in the future, fetch from the LLC. So we wanted to find a way to probe whether number 1 or number 2 is happening, and that led us to these value propagation tests. These are very similar to the message passing tests, and how it happens is as follows. Both producer and consumer cache this value of x equals 0. Then the producer runs first, writing x, updating y. And then at some time later, the consumer runs. And we know it's sometime later because it's polling on y. So when y equals 1, it will proceed with operation 4, which is the load of x. You'll notice the lack of synchronizing operations here. And that's because we want to see what the hardware does generally. So now based on the value we read, whether it's 1 or 0, we know that either it's reading the updated value from the producer, therefore a more SWMR-like protocol, or if we read the stale value of 0, we know that the consumer, there are invalidations didn't happen by the producer, and the consumer has to do more work to read the updated values. So this way, it's a philosophical dual to the message passing litmus tests, where we deterministically figure out what the actual underlying hardware mechanisms are that are at play all the time. So we first test the Hopper GPU on its own, and we ask whether it uses writer-initiated invalidations, the primary question. And we saw the pattern. We use GPU-scoped operations for the y values, so we are forced to read and write from the L2. But the load of x does give us the value of 0, which means that even though the GPU scope load of y read from the L2, and we've updated that, we're reading the cached stale value in our L1. Then we ask, what about the store operation itself? Is there a write-through mechanism or a write-back mechanism? So we disable the caching, and we run the same test. This time, we notice that the load of x always reads the correct value of 1. And because it wasn't cached in the L1, it necessarily has to read from the L2. And even though the store of x by the producer was unscoped, it is being written through to the L2 cache. Then does the Hopper self-invalidate on an acquire, the third piece of the puzzle for that number 2 class of coherence protocols. Here we use a GPU-scoped acquire for the flag value of y. We bring back caching, and we always read the correct value of x equals 1, which means that when this acquire happens, the L1 cache is invalidated, and we are forced to fetch from the L2. Now that we've covered the GPU, we come back to the CPU-GPU system, and we ask the following questions. Does the Grace CPU invalidate the Hopper GPU, and vice versa? So again, same test, but now the producer is on the CPU. The consumer caches, GPU-scoped load on y, and we specifically issue a CTA-scoped load on x. And we notice that the CTA-scoped load always yields the stale value of 0. But if we change this operation, the load operation x, to a GPU scope and force reading from the L2, we start seeing the correct value of 1. This means that the Grace invalidates Hopper's L2, but not the L1. The Hopper GPU also actually invalidates the Grace CPU caches across the hierarchies, and we always see the updated value of x equals 1. So that kind of settles the coherence question. Writers don't invalidate, write through L1 caches, L1 self-invalidated on an acquire, and then for the heterogeneous cases, they are selectively invalidating the other caches. We also notice a surprising result with the read modify writes, where we run this test with 2 counters, one on the CPU, one on the GPU, 1 billion iterations. At the end, we expect to see the correct value of 2 billion. And with a system scope fetch and add, it is morally strong. We always see the correct value of 2 billion. But with a narrower scope, like the CTA or the GPU scope, we no longer have that guarantee. So the result might not necessarily be 2 billion. But in our tests, we do notice that the result is always correct, irrespective of the scope used, suggesting that the RMW implementation is much stronger than the specification, both for the PTX GPU on its own, as well as for this ARM PTX compound system. And this is explained by the Amba-Chai FAR atomics, which do not lock a cache line to update it, but rather perform the incrementing operation at memory itself. So the cores will send the request to the directory or the interconnect, and the interconnect will perform the update in the resident memory. And if you're a performance programmer, the stronger than spec RMWs are not guaranteed by the model, so use them cautiously because the implementation can change anytime. For a compiler writer, these compound memory consistency models lead to this, the notion that independent compilation is empirically safe. And as a hardware architect, you can learn that
we don't have too much time, so maybe one question. Anyone? Okay. Then can I ask one brief question? Did you contact NVIDIA and get confirmed?
Yeah, go ahead.
Did you contact NVIDIA and did they confirm?
Yeah, so we have been in touch with NVIDIA, and the thing is they can't really confirm these or publicly release these because they want to have the flexibility to adjust the implementation for the next iteration, but they haven't denied that any of this is correct. And we're actually trying to work with them to formalize this compound memory consistency models because I'm sure a lot of you know about the Grace Blackwell machines, which are running all of our training data sets, and those use a very similar architecture. So yeah, we're in touch with them, yes.
Okay, great. Let's thank the speaker again.
Thank you.
This is the end of this session, and we'll have a 20-minute break, and then there will be last session.
of ISMM, and yep, we're going to have a great few papers here. My name's Steve Blackburn. I'm going to be the session chair, and without further ado, we're going to hear from Nadav Amit about enabling huge pages for real-world executables. So thank you.
So I hope we are all awake at this time of the day. Let's talk about huge pages and huge pages for code. Why should we care about it? Well, as you know, every instruction that we need to execute, the first thing, the CPU needs to read it, needs to fetch it. And for doing so, it needs to translate its virtual address into physical one. Now, this translation can, in the worst case, require 5 levels of indirection, so we need potentially to do 5 memory accesses. Obviously, this is too slow. So the solution the CPU employs is to hold the cache for those translations, which is called TLB, Translation Look Aside Buffer, or more specifically in this case, an instruction TLB, ITLB. The ITLB is really important, potentially, not potentially, in fact, more than the DTLB, than the data TLB, because if we don't have the next instruction, the out-of-order execution cannot hide the latency because we don't know what else we are supposed to do. Huge pages attack this directly by using a page of 2 megabytes instead of a page of 4 kilobytes. The ITLB miss rate can drop dramatically because the ITLB can cover a much bigger code base. Now, in the past, huge pages were not really used for code very often, and this could be explained by poor support of the hardware. Hardware did not have too many entries dedicated for huge pages. But this was a decade ago. This is not the situation anymore, and still, most of the executables you use these days do not use huge pages for the code. And we wanted to look at this problem to see why it is so and how we can do it magically today without changing the operating system, without changing the loader, how we can get huge pages with existing executables without relinking them. So let's talk about why it is so hard, why we don't have huge pages today. Well, 3 layers must agree in order for us to have huge pages. And I'm talking in this talk about Linux, but this is not specific for Linux. So the first thing we need to have is a file, the executable itself, that needs to be huge page friendly, let's call it, and we'll talk about it in a second. And beside that, we have the dynamic loader that is supposed to map the executable to memory. And we have the kernel that has page cache that holds those mappings of the file. They need to map the executable, the code, using 2 megabyte page. But even if the executable is mapped with 2 megabyte pages, even if the executable is huge page friendly, this does not happen in practice for reasons that the loader does not have a good facilities to convey to the operating system that it wants 2 megabyte pages for the code. And the operating system itself, sometimes, even if it gets the right hints, it doesn't employ 2 megabyte pages. And we'll talk about the reasons for that. So let's talk about the requirements from the executable. What do we need from an executable in order for it to be mapped using huge pages? The first thing that we need is what we call offset alignment. The offset where the code sits within 2 megabyte chunk must be the same in 3 places. In the file, in the physical memory, because the page cache lays each 2 megabytes in such a way. And at the virtual address, it also needs to have the same offset within the 2 megabytes within the huge page, because that's what the hardware imposes. So if we have any disagreement on this offset in the file and the virtual address that we need to set the huge page, a huge page will not be formed. The second thing that we need to have is segment separation. This is probably more intuitive for you. This is a hardware requirement. Each page must have this very specific protection, which means that we cannot have in the same 2 megabyte region both read-only and read-execute pieces together. Now, the first requirement of offset alignment that I mentioned is, in most cases, not all, easy to obtain by just editing the executable alignment requirements. This is something that you can do with obj copy. But getting a segment separation is much harder. And why is it so hard? You may say executables are relocatable, so we can maybe move the code segment out of where it is and put it in a different place on a huge page. And to understand the problem, let's have a look at how executables are being laid out, as we can see here an example for an executable. So the ELF, the executable in this figure, has a header, and then it is composed for multiple segments. Usually the first one is metadata segment that has all kind of information like the dynamic symbols, and followed by several more segments, the code segment that come usually right after, the read-only segment after that, and so on. Now, while we can relocate, while executables are usually position independent, and we can relocate them, we cannot relocate separate segments. And the reason for that is that we have cross-segment pointers. So if we have this pointer and we decide to put the segment elsewhere, the execution will not succeed. We will have a broken executable. Now, there are tools that do that, like tools like Bolt, LLVM Bolt, if you heard about that. However, those tools are usually doing all kind of disassembly based on all various heuristics, and as a result, they might fail. In our experiments, only glibc, which is a very common library, LLVM Bolt failed. Obviously, we can do relinking, but doing relinking requires us to have access to the source code or the objects that are generated, and this is much more complicated for many deployments. If we look on existing solutions that are being used in real life, we see two kind of categories. We have copy and remap solutions and file-backed solutions. Copy and remap, which are actual solutions that are being used in real life, like libutilbfs and Intel's IODLR tool, do the following. They copy the code into fresh aligned anonymous huge page, and then they remap this region on top of the executable that they had before. By doing so, they sidestep all the problems that the page cache has, all kind of limitations that the page cache has, but they also lose the semantics of a file, because now this memory is anonymous. As a result, we don't have any more cross-process memory sharing, and we cannot reclaim memory without swapping it out, because now it's anonymous. Profilers and debuggers do not work anymore, at least not out of the box, because we don't have symbols, because we don't know that this is actually coming from a file. When we tried libutilbfs, we also found all kinds of bugs in it, so clearly it's not really used a lot. Intel's IODLR also, unfortunately, was recently discontinued with all kinds of Intel changes. On the other side, we have solutions which are file-backed. The most prominent solution is read-only THP, read-only transparent huge pages. This is a feature that you can compile, you can build your kernel, and it will allow the operating system, by special casing the case of executable code, to more easily form huge pages for code. Let's say that in so many words. It will do it lazily. So first you will get 4 kilobyte pages for the code, and then it will promote it to 2 megabytes. But it does not, like all the other solutions that we have here, it does not handle the segment separation requirement. So you cannot still map a page that is half, if you have a page that is half code and half data, this cannot be mapped into memory. So we wanted a solution that can be deployed today. Does not require relinking as shown here, and we have something like that. So what basically we are doing? So the insight that we have is that although we cannot move segments without having all kind of relinking,
we can shift memory, we can shift part of the executable. And if we shift the right part, we can do so without knowing anything about the executable other than standard ELF layout, standard executable layout. Afterwards, we have the problem that in order to have the executable mapped into memory correctly, we need to preload it into memory in such a way that accesses afterwards will get 2 megabyte formed pages. We'll show later how we do it. When the memory is being loaded into the page cache using huge pages, when the stock loader, we are not changing the dynamic loader, later try to map the page into the executable, it will get huge pages. So the first thing that I need to explain is how do we do this magic, in a sense, of getting huge page. We can see here the original layout of glibc and how we are changing it. And the secret is that while we cannot move arbitrary segments, the code segment that is usually the second segment coming after the metadata can be shifted with all the other segments downwards. And the reason is that the metadata segment, which is the dynamic symbols and the relocation information, has a very well-defined structure. So finding cross pointers from the metadata is possible. And there are no pointers coming into the metadata from the other segments. By shifting all of those segments downwards, adding padding of trap instructions, of course, to prevent any warp gadget injection usage, we can shift all the code downwards and have a huge page that is purely code. The second problem that we have is that sometimes, because there are all kind of, the page cache has a policy of bringing stuff as 2 megabyte pages that is suitable for data and not for code, then many times we will not get huge page even if we set the executable in the right way. So to do so, we need to convince the page cache to give us 2 megabyte page to prefetch 2 megabyte segments and to map those as huge page later on. Therefore, we have a dispatcher running before the executable itself, prefetching sequential 2 megabyte segments using reads. It then maps those segments into its memory and checks that it actually got huge pages using procfs information. Sometimes it wouldn't get huge pages because of all kinds of operating systems shenanigans. In that case, it will use advice, it will use services in order to evict the pages that it got into the memory because it got 4 kilobyte pages. And right now, Linux does not know in a regular file system to take those 4 pages and convert them into 2 megabyte pages afterwards. So we want to evict them in order to bring them back as 2 megabytes. I'm not regarding read-only THP. This is a hack that is soon to be obsolete in the operating system. Finally, we have the story of DL open. We need to handle cases in which executables are being loaded later on, and we do it using a hook that is called LD audit, similar to LD preload that was discussed before. So let's talk about evaluation. We ran many benchmarks. We ran we ran 6 benchmarks, 2 databases, 2 web servers, and 2 compilers. We ran them on both x86 and ARM CPUs to see the behavior. Because of the shortage of the time, I will try to be a bit brief. Looking at Node.js, we ran a web server on Node.js. On the left side, on the left pane, we can see the performance. The higher, the better. And we can see that we compare 5 setups. We have the baseline Linux. We have 2 copy and remap configurations that use anonymous memory for the file instead of the page cache. And we have the 2 configurations that we compare against, the read-only THP, this emerging and soon to be obsolete Linux feature, and our solution. On the right pane, we can see how many TLB misses we have. We have it in misses per kilo instructions. We have the ITLB, which is the level 1 TLB, and the STLB, which is the second level TLB. When we compare the libhuge-TLBFS and IODLR to baseline, we see that libhuge-TLBFS does not provide any benefit in this workload. And that the reason for that is that this workload is dominated by libraries. And libhuge-TLBFS does not promote libraries to use huge pages. IODLR provides relatively good performance benefit of almost 9%. However, as I said before, this approach of copy on remap has a lot of implications on the uses of this feature, of the executable. No profiling and no sharing of memory for processes. When we look at the read-only THP, we see that performance is not that great, and there is only 4% performance improvement, and we have a very high variance, and partially we attribute it to the fact that promotion with our OTHP, there is promotion of 4 kilobyte pages into 2 megabyte, but it happens asynchronously, it happens lazily later during the runtime of the workload. Finally, our solution provides a speed up of over 11%. And it also reduces the ITLB misses to practically, to virtually zero. With the Apache web server, we can see that that all the solutions other than ours do not provide any meaningful performance improvement. And the reason for that is that most of the libraries almost all the libraries that Apache web server uses are very small. And because of that, there is no benefit of, there is no potential to get any performance improvement. There is no potential for forming 2 megabyte pages without any meaningful shifting of the code to allow segment separation. Our solution, as shown, provides 5.2 performance improvements. And unlike other workloads, this is pretty much the only workload in which we don't have a virtual zero ITLB misses. One point that is worth mentioning is the question of whether every binary should get huge pages. And obviously, if we do that, because of the shifting that we need to do, we might waste a lot of memory if we do it for each library. Apache can have over 200 libraries being loaded. So we decided that we will try to do it only for executables for objects that are bigger than 1 megabyte. And skipping the small libraries showed that it's not only beneficial from memory point of view, it also can even improve performance. We can see in the ARM case, the Apache server even providing performance degradation if we try to promote all the libraries to use 2 megabyte pages. And the reason for that, according to our understanding, is that we got all kind of thrashing on the branch predictor. It was not related to the TLB at least, because we didn't see any degradation in the ITLB and STLB MPKI in the misses per kilo instructions. To summarize, to conclude, we saw the code huge pages blocked in 3 layers, and we saw that we can actually deliver today a solution that provides you huge pages for your executables without changing the operating system, without changing the loader, and without access to the source code. Now, solutions are coming. There are solutions that come to your to Linux, but we were promised that before, and now we know that it's possible at least to do it today. Thank you, and I'm happy to take your questions.
I think they're very interesting work. So you mentioned in the beginning that you pad the code to make it 4 megabyte aligned. But what is it possible that the end of the code going to overlap with some data, read-only data or read-write data, and then you make this 4 megabytes of memory in one page, and the code should be read-only and executable, and the read and write data it's kind of messed up. Is this possible?
So there are limitations that, because of the time I didn't mention. We are relying on the common patterns that we saw for executables. And we saw all kinds of patterns. And what we saw in all of them is that the code usually comes first.
Right.
And because of that, we can just shift the code forward. So I don't know if I answered your question, because to be fair, I'm not sure that I fully understood it. But if we shift the code forward and we didn't have the data before, then nothing breaks after.
But what if the data and the code share 1 4 megabyte of huge page? 2 megabyte of huge page. So because you have to apply the permission for the code, and then you're going to make the data as read-only. Is this possible, or?
We are not. I'm sorry. Let's take it offline. I'm sorry. I'm not sure that I fully understood. I'm sorry for that.
Oh, I had actually a very similar question. So if you don't mind, but maybe I can make it more concrete. If you go to the left image there.
To the left image.
The leftmost, right? So, just where you were, right? So if you take that code, you can't just simply slide it down a few bytes, because then you hit the read-only data, right? So you're talking about moving it down a substantial amount into a new page.
Read-only data is not backed by 2 megabyte pages. It's backed by 4 kilobyte pages. So I can just shift it down.
Okay. So you, right. Okay. So you.
There are no 2 megabyte regions in the executables today.
Right.
In most executables. So I'm not breaking a 2 megabyte just to provide 2 megabyte for the code. But even if I did, it would have been beneficial, because code is the part of the executables that benefits most from
right. But the virtual address for the code will not clash with the virtual address for the read-only
No,
data.
I'm going to shift everything down, because I kept the relative offsets the same. Everything shifts down. Okay? I shifted everything down. There is no collapse. There is no collision.
Right, but you've very carefully moved the last, and I think this answers the last question. At the bottom there, you've taken very careful. You've been very carefully moving the code so that the read-only and the read-write are spilling onto different 4K pages.
The read-only and read-write were aligned to 4 kilobyte pages before, and I didn't break it. I didn't change it.
Yeah.
I hope it answered your question.
Yeah, I think. Other questions? That was super interesting. Thank you.
Thank you.
Sorry. So our next speaker is Mohammed Hussein, who's at Virginia Tech. At AMD. Where are you located? You're an ARM. Sorry. Yeah. Who did the work while at Virginia Tech, but now is at ARM. And he's going to talk about Stretch, which is a fault-driven DSM runtime for distributed multi-threaded applications. So thank you.
So, good afternoon, everyone. Good afternoon, everyone. I'm Mohammed Hussain. Today, I will be presenting Stretch, a fault-driven distributed shared memory runtime for multi-threaded applications. So, this is a joint work with Eduardo D'Alessio and Professor Shuang Wang and Professor Binay Ravindran. So the quick roadmap for this presentation. So I will motivate why we are revisiting shared memory now, and then I cover the two Linux primitives the Stretch is built on, and walk through the design and coherence protocol, show the implementation, and then I'll spend some of our time on the evaluation. So let's start with why DSM is worth revisiting at all. So the modern applications are like compute and memory intensive, so they increasingly outgrow what a single machine can offer. The natural fix is to scale out, but for conventional multi-threaded software, that's surprisingly hard. Today, you have two options. You rewrite the application for message passing, like MPI, or rely on heavy kernel support. But both hurt deployability. The distributed shared memory offers a third path. It preserves the shared programming memory model while letting the memory span across machines. But the DSM is not a new idea. So the classic systems came with like strong assumptions like kernel modification, special hardware, or specific language and compiler support. So the question we ask is like, how far can a Linux user space interfaces take a deployable DSM runtime for existing multi-threaded application? So two things make the question timely. The hardware landscape shifted in DSM's favor. So the DRAM latency has been flat for like 3 decades, and network latency improved by like orders of magnitude. Take RDMA for instance. So RDMA now brings a remote memory within the order of magnitude of local DRAM. And the user for FD in Linux let us handle the page faults entirely in user space. So the classic DSM never had this design options. So to answer that question without modifying the kernel, we lean on a handful of Linux primitives. So everything here ships in a stock kernel. So 5 pieces for like 2 jobs. For memory coherence, we have user fault FT that intercepts page faults in user space, and process VM ready and write V copies pages between the processes. So we have process madwise that let us invalidate a page in another process, and kprobe helps trigger that invalidation cheaply. For execution placement, so CREW checkpoints and restores the full process state. So the takeaway here is like no custom kernel module or driver or patch, just the interfaces, they are already there. So 2 of these do the heavy lifting. So let me spend a moment on each. So user for FT first. Normally when a thread touches a page that isn't there, kernel handles a fault. So user for FT flips that. A processor can register a memory region and have the page first delivered to it, and then resolve them from the user space instead. So it means we can turn any ordinary memory access into a protocol event, even without touching the kernel. Now there are 3 kinds of page fault. Let's see which one handles user for FT handles. So first one is the not present fault, which means there is address mappings, but there is no resident frame. And the second one is the protection fault. So this is like an access violation. It's mostly like a write to a read-only copy. And the third one is the addressing fault. So there is an address doesn't have any value mapping at all. So it is just a bug, and it's delivered as a segmentation fault. For stretch, the first 2 are exactly the events we need. So a not present fault tells us the page is missing or it has been invalidated. A protection fault is a write to a read-only copy. So this is how we detect a remote write before it even happens. So those maps directly into 2 transitions of our MSA protocol we care about. You fetch a page and invalidate the others. The third category is not a coherent event, so we just let it pass as a normal. So the user for FT handles the memory. To run the thread on other machines, we also have to move execution. So that's solved by CREW. So CREW is the checkpoint and restore in user space. So how the CREW works is like it freezes the running process and saves it the entire file, entire metadata and the process components into a disk. You have like the memory maps, the threads, and the open files and everything. So you will use it to bring it back to life. And just like user for FD, there is no kernel patch. So the workflow on the slide is the standard one. You checkpoint a process into a set of image files, and then you transfer those files over the network, and then you restore them on another machine. So what stretch needs is different. So what stretch needs is different. We want to take an arbitrary set of threads and then restore them on a remote node, while we keep the rest of the threads running on. So that's what turns the CREW, a migration tool, into a thread placement component for the distributed execution. So the division of labor is thus. So the CREW moves the execution context onto different machines, and the DSM runtime, which I will describe next, keep the shared pages coherent. So with those primitives in hand, let me show how the stretch composes into your system. So we have 2 nodes here, the DSM server and the DSM client. So DSM server is the central coordinator. It tracks the status of every shared page and who owns it and handles all the coherence messages. So every other node runs the DSM client. So the DSM client runs the application threads, catch their faults via user for FD, and installs or invalidates page using process VM ready. So the workflow in the diagram is what we just covered. You checkpoint the process, transform the crew images, and restore the threads across nodes. With cross ISA migration using Popcorn compiler suite, those nodes can be x86. So you dump a process from an x86 and you can restore it in an ARM node. So for the coherence is at the page granularity. So every page is like modified, shared, or invalid. The writes are enforced via page granularity. We register like shared regions either automatically or manually. So the Linux exposes the procfs, and then the procfs exposes the kernel mapping, the page mapping, so that we can register it automatically, or we can register manually. Like in the evaluation, we use the manual selection. So the faults we measure reflect the intended sharing, not the allocated noise. So let me dive deep into the DSM components. So each node here has the same internal structure. You have a local fault handler for its own threads faults, and a remote fault handler for messages that arrive from the other nodes. So on the local node, this lives into the DSM server, on remote nodes inside the DSM client. So everything flows to the message layer in the middle, and there are only three kinds of traffic, like the page request, page ownership transfer, and then synchronization. So DSM's client is the server's counterpart on every remote node, but it doesn't make no coherence decision of its own. It catches its threads faults with its own user for FD handler and forwards them to the server, and then applies whatever the server decides. So it could be installing a fetched page or invalidating a stale copy on behalf of the local thread. So the thing to notice here is the topology. So the client only ever talks to the server, never to each other. So this is a deliberate decision we made. So it gives the server one serialized authority view of all coherence. So this keeps the protocol correct and simple, and the trade-off is that the server sits on the control path. So it's a CPU that became a performance factor. You will see that in the evaluation. So what does the server actually do? So it stacks the page ownership table, the status of every tracked page across the nodes. So as part of the DSM, we have an MSI-based coherency protocol that is implemented at the page level to track each page status. So each page can have like three possible states: the modified, shared, and invalid. So if the page is in the modified state, then the particular node has the exclusive right access to that page. So the node is also flagged as the owner of that particular page. A shared state indicates that node has the read access to that page. So one or more nodes can have an identical copies. They are collectively called as the owners of that page. So there is also the invalid state. So if the node tries to read or write to an invalid page, it triggers a page fault with user fault FD, and the latest copy of the page will be transferred to that node. So now the actual page ownership table. So this is the server's authority view of the world. There's one row per shared page, all from the local node's perspective. So the page states here are modified, shared, or invalid, and who owns it, and which nodes hold the shared copies. So the first page in the row, the status is modified, and the owner is the local node. So it has the only writable copies, and every other node is marked stale, since the local node is the executive writer. Next, the second page is in the shared state, which means the identical copies of the page exist in multiple nodes, called as the shared owners. Third, we have an invalid page. This is from the local node's point of view, and the owner is in the remote node 1. So the local node doesn't have a valid page. So if a thread from the local node tries to access it, the DSM server knows where the page resides and try to access it, retrieve it. The shared rows in the second and fourth row, it has like multiple owners, and all are marked as a read only. So anyone can read, so nobody can write without the first invalidating the other shared owners. The thing is, this is that at max there's only one writable copy of any page exists at a time, and because every fault routes through this one table on one server, this is where the centralization cost lives. So which is why the results show the server CPU is the sink factor. Now I will give an example of missing page fault and how it is handled by the DSM runtime. So the application thread on the remote node 1 falls on a particular page, so it is a missing page fault. Its local fault handler turns it into a page request, and the page request is sent across the message layer to the server. And then the server consults its own page ownership table, and it sends the get remote page message to fetch the page from the remote node. And then the remote node ships the page back to the DSM server, and then to the remote node 1, and the original requested, and then which resolves the page fault. So the synchronization is built on the same fault mechanism. I will explain the barrier protocol. The nice property here is that synchronization uses the exact same fault mechanism. So the barrier page is just another user for every registered page. So these faults we interpret as synchronization events instead of coherence request. There are no new channel or extra kernel mechanism. I will walk through the 5-phase barrier protocol. First, we have a local barrier. So threads within each node sync locally first. So all the internode work is finished before any cross-node communication starts. The global barrier. So as shown in the diagram on the left, there is one representative thread per nodes falls in the barrier page, sending the barrier hit to the server, and the server waits for all nodes and then release to each. So page exchange. So between the two global barriers, node falls in the shared pages they will need next, and then that's the page fault and the page data exchange in the middle. So everyone has a consistent copies before receiving. And then we have like a global barrier confirm. So the representative thread fault again to the signal page exchange is complete, and then the server confirms that all nodes are done. So each node releases its local threads, and then the computation resumes. So the picture on the left is the key idea I'm trying to convey. So there are many local threads, but there is only one representative thread per node that actually talks to the server. So that's what keeps the barrier traffic proportional to the number of nodes and not the number of threads. And to cover the mutexes, the mutex also follow the same pattern. You occur locally and then write fault on the dedicated block page, and then the server serializes the request and grants to one client. And there is a second fault for unlock. So this is best for like coarse-grained critical checksums, since each occur causes a round-trip message through the message layer. Because it's all handled through the fault, there is no exchange in the application code. It's run fine even without the stretch actually. So that's the design. So next question is how it performs. So I will start with the cost of a single coherence operation. So for this experiment, we have 3 nodes. A server acts as a coherence authority, one client holding a page and one client requesting it. We measure the round-trip latency of a single page ownership transfer over TCP and RDMA, and we'll see the number of cores we give the server. At single core, RDMA is actually worse than TCP. So 300 milliseconds compared to 225 for TCP. So RDMA is supposed to be the fast path. The reason is that our RDMA path relies on busy polling on a completion queue. So with only one core, the polling contents with the fault handler and then application for the same CPU. So RDMA only pays off when you dedicate cores to the DSM server. So if you have any core pressure, the plain PCB is the safer choice. So that's the cost for like one operation. The real question is like how it works for a full application. Let me explain the experiment setup. So we have like 2 setups, the homogeneous one and the heterogeneous one. So on the left, we have the homogeneous cluster. This is 4 identical AMD EPIC servers on Cloud Lab. So one DSM server, 3 clients connected over ConnectX network cards, and we run both TCP and RDMA here. This is where we measure execution time and measure scaling on the Phoenix suite. On the right, we have the heterogeneous cluster, and Intel Xeon as the main x86 node plus 4 Raspberry Pi ARM boards, and they act as a worker node, and they are all connected over TCP. Here we measure 2 things. One is the execution time, and then the energy efficiency. Since the whole point of offloading to the lower power is the lower power ARM board is the energy angle. The first setup answers the question like, does our page granularity DSM scale on what sort of access pattern? And the second one answers a different question. Does this coherence runtime work across architectures? So let's start with the scaling question. So Phoenix benchmark on the homogeneous cluster. So in this evaluation, we found one factor that predicts the performance. That is the computation to page fault ratio. So how much useful work you do per fetched page versus the cost of servicing that page fault. So everything you see on the chart traces back to that one ratio. So here the clear winner is the matrix multiply. It is like a 300 times faster than the single node execution. So each fetched page involves a huge amount of floating point work before the next fault. So you have a high ratios, we also have a high clean scaling. This is the strong use case for stretch. So the PCA is the middle case and interesting one. The number needed is the work balance thread placement. If you do a nice equal split of threads, you barely get 1.5 times speed up. So because the early threads handle the proportionally more work, so the placement strategy matters, not just the thread count. So the other benchmarks, the word count, the histogram, linear regression, so all are in the 3 into 4x range. The thing is, like, a lot of that is a weak single core baseline rather than a scalable DSM. That's why they are high. So the word count, the 4 times speed up is the highest number in this evaluation, but it collapses to below 1 once the core is saturated. So at low core counts, they are not scalable. And the one in the blue bar, that's the k-mean. So it also has a lower than a single machine. So here in this benchmark, the centroid updates access the shared pages a lot in tight loops. So the write invalidation dominates the message transfer time. The problem is the fine-grained write sharing, and it is incompatible for the page granularity coherence. So no matter which transport you use, yeah, the fine-grained write sharing messes up. So we are showing the case where this works and for which workloads it doesn't work or performs poorly. So that's for the homogeneous scaling. Yeah, let's see how it works for heterogeneous system. So we have like Xeon on the Raspberry Pi 4. So the workloads is from the popcorn suit, the Black-Scholes, the grep, and matrix multiply. And the thread state is like translated across ISIs with the popcorn suit from x86 to ARM at the migration time. So the left chart you see here is the execution times. So it drops as we add more remote ARM nodes. So we have like 1 local node and 1 remote node, and then 2 remote nodes and 3 remote nodes. The bar shows like the scalar working even when the workers are in a different architecture than the main node. So in the right chart, this is the energy efficiency in jobs per kilojoule. So the matrix multiply improves like 22% and grep by 14% by offloading to the low power ARM cores. So but the headline here is not the speed up or the energy numbers, it's the correctness. So you have the same coherence runtime that operates on unmodified across x86 and ARM. So the memory behavior is identical to the homogeneous case here. The only extra cost is like the one-time context transformation at migration. So heterogeneity is the capability we can get for free from the stretch. So but we don't need a separate system. So let me put all of this together. There are 3 things to take away here. So the modern Linux primitives, the user-fault FT, the MadWays, and the CREO are enough to build a deployable user-space DSM with no kernel patches. So that was the open question here, and the answer is yes. And second, it works well for the compute-heavy, coarse-grained sharing workloads. But for fine-grained write sharing, it's still a fundamental challenge at page granularity. To get the benefits of RDMA, you need dedicated server cores. Otherwise, the TCP wins. So Linux gives enough to make a DSM deployable again, as long as you respect where the page granularity breaks down. Yeah, so we have the code for our work. So and thank you, and thanks to the anonymous reviewers and ISM organizers.
Thank you. We have time for some questions.
Interesting talk. I have a couple of questions. So I was wondering about 2 issues, right? So like, how do you implement read, modify, write instructions like a compare and swap, which original shared memory programs have? That was my first question. And the second question is, what's the story about failures, right? In case any nodes fail in a distributed setting, then your protocol might block, right? So how do you handle that?
Yeah, there is a really good questions. Like, so when we started thinking about the synchronization and so multi-threading comparisons, like, so we just want to showcase like what is the practicality of this this interfaces that's given by the Linux kernel, so that we can create a deployable DSM runtime. So we just concentrate on the most common ones, the barrier and the mutexes. So we didn't think about the conditional variables or the Aquarius logs. Yeah, so I don't think there is any interfaces that's in Linux that allows to do that. Like that might require a heavy change in either in the kernel, or like it might need a lot of work in the compiler, or we just go with the MPA based libraries to do that. And for your second question, yeah, so if any of the server fails, yeah, the whole system, not the server, even the client fails, the whole system fails. Like, yeah, we didn't think about in the point of fault tolerance or in any way. Like, we didn't even think about in the way of security. So we only saw it as the point of the practicality of the how to create a DSM system just with the modern tool that Linux offers. I hope that answers your question.
We've still got time.
Very interesting talk. I wonder, you did not monitor any event other than the page fault from the point of view of user fault FD.
Yeah.
Why did you choose not to? I mean, you could have done a different thing of being cooperative user fault FD, not outside of the process, but you decided both to be outside of the process in a non-cooperative user fault FD and not to monitor other events. So what's the benefit of that?
So what do you mean the other events? That I couldn't understand the question.
A simpler solution would have been to use user fault FD, but to be part of the application, some kind of parasite code. The other solution would be to sit outside of the application, but to monitor other user fault FD events like remapping, unmapping, in order to support wider events, more diverse events. But you chose not to do either one of those. Can you explain the rationale?
Actually, so in the first versions, we actually used the compile plugin that is part of the crew. Like this is like a parasite code, like that sits outside, but that incurs like a lot of lot of overhead. So we went with the process madwise. When I first started working out, you can't use the madwise event on another process. You can only do it on their own process. So we just and then after then the Linux introduced the way to change the page level modification with the process madwise. So yeah, we ended up using that. Yeah, in fact we tried that parasite code, but there's a lot of overhead.
Okay, thank you.
Great. Let's thank Mohammed for the talk. And our next talk, and the very last talk of ISMM 2026, is going to be from Bijan Tabatawal, and he's going to talk about Bandwidth Speaks, We Listen, Dynamic Memory Interleaving for Tiering. Thank you.
Hi, hello. I'm Bijan Tabatabai, graduate student from University of Wisconsin-Madison, and today I'll be talking about our work on dynamically interleaving data to make effective use of a system's memory bandwidth. This work was done in collaboration with Micron. So memory scaling is not really keeping up with compute. On this graph, we see that the number of CPU cores on processors shown in purple is growing at a fast rate. However, memory capacity per core, shown in blue, is not quite keeping up. Similar trends are true for bandwidth per core as well. Luckily, CXL is a relatively new memory technology that aims to address these scaling issues. So CXL is a protocol that allows for cache-coherent memory expanders over the PCIe physical layer. This allows systems to more cheaply add memory capacity compared to adding a new memory channel, helping alleviate scaling issues. Similarly, it increases the bandwidth available on the system. However, it comes at the cost of higher access latency when compared to local DDR memory, which can lead to significant performance penalties if not used correctly. So the typical way that systems make use of CXL is called memory tiering, which makes use of the expanded memory capacity while minimizing the access latency. Memory tiering does this by first identifying which pages of memory are frequently accessed or hot and infrequently accessed or cold. With that information, the system makes sure to promote the hot pages to local memory and demote cold pages to CXL memory when the local memory is full. That way, in the common case, memory access go to local memory while still using the capacity of the slower CXL memory. This is similar to caching, with the main difference that data can be accessed directly from CXL without bringing it into local memory first. So tiering works well when the bandwidth of local memory is underutilized. However, when running bandwidth-intensive workloads, such as maybe matrix multiplication, putting all the hot data in local memory will oversaturate the local bandwidth while leaving the CXL bandwidth underutilized, leaving performance on the table. The solution to this is to interleave the hot pages between the local and CXL memory when under bandwidth pressure. That way, the system can utilize the combined bandwidth of the system. The current way to do this that's available in systems today is static interleaving. With static interleaving, the user specifies a system-wide ratio to allocate application pages with across local and CXL memory. However, because pages are not moved after they are allocated, static interleaving cannot adjust to changes in workload behavior. So, for example, imagine we have some oracle that knows all of this and decides the static interleave ratio for each workload individually. If a workload begins that uses only 75% of the local bandwidth, the oracle will just put all of the application pages in local memory. If another identical workload begins, the oracle will interleave its pages to utilize the aggregate bandwidth of the system. Currently, this is all fine and good. But if the first workload terminates, the local bandwidth is now left underutilized, and the second workload suffers from the higher CXL access latency for no reason. So what we want is a memory policy that dynamically interleaves application data between local and CXL memory based on the bandwidth demand of the system. A potential solution is a research system called Colloid. When under memory contention, Colloid will migrate pages until the access latencies of both nodes are equal, which will minimize the average access latency to memory. I'll demonstrate how this works with these example mock bandwidth latency plots. So Colloid starts, like other tiered memory systems, by placing all the data in local memory. As traffic goes to local memory, it goes up this bandwidth latency plot. If enough traffic is sent to the local node, its latency will be higher than that of the remote node. Colloid will detect this and then migrate hot pages from local to remote memory until the latencies are about equal. Consequently, the bandwidth utilization of the system increases. The problem with this is that when under bandwidth pressure, such as i.e. after the knee in this bandwidth latency plot, small changes in bandwidth result in large changes in latency, making the calibration difficult. So this can be seen by looking at the bandwidth utilization of Colloid when running the bandwidth-intensive LBM workload compared to using the ideal static interleaving ratio for the workload. The bandwidth utilization when using the ideal static interleaving ratio for this workload, shown on the left, is quite stable at around 425 gigabytes per second of total bandwidth. However, Colloid's bandwidth utilization, shown on the right, is much more erratic. Because Colloid keeps moving data back and forth from local and remote memory, as a result, it only uses about maybe 350 gigabytes per second of bandwidth on average, and is 37% slower than the ideal static interleave ratio. So Colloid is not really sufficient for bandwidth-intensive applications. It's leaving a lot of performance on the table. We want a new policy that treats bandwidth as a first-class priority and not just a convenient side effect. We propose a policy that does this called dynamic memory interleaving, or DMI. So let's talk about its design. So the goal of DMI is to maximize the system's bandwidth utilization, which we found experimentally results in performance much closer to the ideal. It does this by continuously adjusting how data is interleaved based on the measured bandwidth utilization. DMI is composed of two parts, the calibrator and the migrator. The calibrator monitors the system's bandwidth utilization and uses that information to determine how much to change the interleave ratio with the step selector, and how often to update the interleave ratio with the interval selector. It is implemented as a user space process. The migrator, which lives in the kernel, takes the ratio calculated from the calibrator and interleaves the application pages to achieve that ratio. The migrator also monitors if local memory is full and demotes cold pages to make room for interleaved hot pages. So the algorithm that the calibrator uses in the step selector to determine the interleave ratio is pretty simple. In this graph, we show the interleave ratio in orange on the left axis and the bandwidth in green on the right axis. The step selector starts conservatively with an interleave ratio of 100% local memory. Then, once a calibration period, it considers the largest sampled bandwidth for that period and changes the interleave ratio by some step size. If the bandwidth for this period is greater than the last, the previous step is considered good, and the step for this period will be the same as the last. Otherwise, if the bandwidth decreases, the step for the period is reversed and has half the magnitude. And eventually, it will zero in on the ideal ratio. If a change to the bandwidth demand is detected, this process is restarted to find the new ideal ratio. So an important parameter for the performance of DMI is how long the calibrator should sample the bandwidth before updating the interleave ratio. We call this parameter the bandwidth measurement interval, and it's determined by the calibrator's interval selector. Unfortunately, the best bandwidth measurement interval depends on the workload being run. We show this by running two bandwidth intensive workloads, Cloverleaf and GapBS SSSP, with DMI using different measurement intervals, fixed measurement intervals. The plots here show the interleave ratio that DMI chooses over time, with the ideal ratio for the workload shown by the horizontal line. With Cloverleaf, a short bandwidth measurement interval of 1 second pretty quickly converges to the ideal ratio. And longer measurement intervals slow convergence, resulting in the longer runtime. Now let's look at the SSSP workload. And note that the grayed out portions here represent the startup portion of the workload. So here, a 1 second bandwidth measurement interval being used results in the calibrator being pretty erratic in choosing the interleave ratio. This is particularly bad because every time the interleave ratio doubles back, we are taking data we just moved to one node back to the other. With longer intervals, the calibrator more smoothly converges to interleave ratio. However, if it's too high, like with the 30 seconds here shown in purple, it will take longer than necessary to converge. So a bandwidth measurement interval that is too small for a workload will work poorly because a calibrator will not have enough context for making a decision. So consider this graph of the bandwidth utilization of the SSSP workload over time with a fixed interleave ratio. So all of the changes in bandwidth are due to the application itself. If the bandwidth measurement interval is too short, the calibrator may not have enough context for the decision. So for example, let's say for one calibration period, we sample the bandwidth in the indicated region, and then we sample this other region for the next. In this situation, the calibrator will only see a drop in bandwidth, but not know if that drop is due to a change in interleave ratio or the workload itself. This results in erratic change in interleave ratio, as we discussed in the previous slide. On the other hand, if the bandwidth measurement interval is too large, as shown on the left, the calibrator will have enough context to converge correctly, but it will take longer than necessary to converge. On the right, we see that the calibrator doesn't reach the ideal interleave ratio before the workload ends. So we noticed that the bandwidth utilization of the workloads we analyze tend to be periodic. So we want some way to identify the fundamental frequency here of the bandwidth utilization to set the bandwidth measurement interval to that. Visually from the graphs, we can see that the fundamental frequency of Cloverleaf is about 2 seconds, and for SSSP is about 10 seconds. But how do we find this programmatically? Well, for that we use the fast Fourier transform, or FFT. The FFT is a mathematical operation that transforms a periodic time-varying function into another function that describes the extent to which certain frequencies are present in the input. Note that while the output of the FFT is often plotted with the x-axis being frequency, we show it as the period because it's a more natural unit for our needs. So for example, here we show a plot of a sine wave with a period of 1 second, and the FFT of that function is non-zero at a period of 1 second and near zero elsewhere. Similarly, FFT of a sine wave with a period of 5 seconds is non-zero at 5 seconds and near zero elsewhere. And if we take the sum of these two signals, the FFT can clearly identify the two component sine waves. So because the bandwidth of the utilization of the workloads is periodic, we use the fast Fourier transform on the bandwidth samples to decide what bandwidth measurement interval to use. So on the left, we show the bandwidth utilization of our workloads Cloverleaf and SSSP over time, which have a fundamental frequency, as I said, of 2 and 10 seconds. And then on the right, we show the corresponding output of their FFT. Again, on the x-axis, we show period instead of frequency. So the FFT of Cloverleaf shows the strongest components at a period of 2 seconds, indicating that's a good choice of the bandwidth measurement interval, which we visually said is true. Similarly, 10 seconds in the FFT for SSSP is the most dominant frequency, so we should use that as our measurement frequency, or measurement interval. Note that while there are other peaks in the FFT due to the bandwidth signals not being perfect sine waves, the fundamental frequency is still easily identifiable as the strongest component. It's important to note, though, that these bandwidth figures on the left are shown with a constant interleave ratio. However, with DMI, the interleave ratio will be changing, which changes our bandwidth measurements. Taking the FFT of a signal that we are modifying leads to some challenges for determining the correct bandwidth measurement interval. For the sake of time, we don't discuss these implementation details to solve them, but they can be found in our paper. So now we'll quickly talk about the migrator. The first of its responsibilities is to decide which pages should be candidates for interleaving. The migrator only chooses hot pages as interleave candidates, ignoring cold pages. This is because, being infrequently used, cold pages don't have a large effect on the bandwidth utilization, not really making them worth the cost of migration. On the other hand, since hot pages are, by definition, accessed frequently, migrating them has a larger effect on the bandwidth utilization of the system. So in addition to interleaving hot pages, it's possible that there may be too many cold pages in the memory node to interleave the pages effectively. In these situations, the cold pages are moved to the other node to make room for hot pages. This also has a useful property that when the interleave ratio is set to 100% local memory, DMI kind of falls back to the traditional tiering, because in that case, all of the hot pages will be moved to local memory while cold pages will be demoted to CXL. So now let's look at the evaluation. So we evaluate this on a 72-core Intel Granite Rapids CPU with 7 DDR5 memory channels totaling 260 gigabytes per second of read-only bandwidth. And we have 8 Micron CZ122 CXL memory expanders totaling 220 gigabytes per second of read-only bandwidth. And we compare the systems to a baseline of the ideal static interleave ratio that we found manually for each workload. So first, we look at how well DMI performs running a single bandwidth-intensive workload that can fit entirely in local memory. And then in addition to evaluating DMI against colloid and the ideal static interleave ratio, we also evaluate against Nomad and HMSDK, which are state-of-the-art traditional tiering systems. So the x-axis of this graph are the workloads being run, and the y-axis represents the runtime of the workload relative to the runtime of just putting all of the workload's data in local memory. So because Nomad and HMSDK leave all the workloads data, hot data in local memory, they don't make use of the CXL bandwidth, making them 50% slower than the ideal case on average. Colloid performs much better than them because it does make use of some of the CXL bandwidth. However, because of its more erratic data placement, it's still on average 27% slower than ideal. On the other hand, because DMI can effectively find the interleave ratio, it performs within 5% of the ideal case on average. So to dig a bit deeper, we look at how well DMI converges to the ideal interleave ratio for a workload compared to colloid. So the x-axis on this graph represents time, the y-axis represents the interleave ratio effectively, and the ideal ratio for the workload is represented by the dashed line here. So colloid, plotted in blue here, is very erratic with its data movement and never really reaches a steady state. On the other hand, DMI, which I plot here in orange, reaches near the ideal interleave ratio in around 30 to 40 seconds and stays there for the rest of the application's runtime. In fact, a majority of the slowdown DMI has compared to the ideal case is due to the time it spends searching for the ideal ratio. So now let's look at evaluate our method of selecting the bandwidth measurement interval using the FFT. So the graph on top shows the interleave ratio chosen by the FFT approach, shown in orange, and the best fixed measurement interval that we found that we tested for this workload. And then the bottom graph here shows the chosen measurement interval when using the FFT approach. So with Cloverleaf, Our FFT approach initially chooses an interval of 2.5 seconds in the beginning, and then 1.5 seconds as the workload speeds up due to having more bandwidth. Using the FFT approach allows DMI to converge about maybe 20 or so seconds after the fixed measurement interval of 1 second. With SSSP, the FFT approach chooses a measurement interval of around 15 seconds, and it converges in about the same time as a fixed interval of 16 seconds, which of the ones we've tested perform the best. As a result, the FFT approach performs within 1% of the best static interval that we found. So however, this approach isn't perfect. The GAP-BS BC workload has a much more erratic bandwidth utilization than Cloverleaf and SSSP. And so like before, with a 1 second measurement interval, it's pretty erratic. And we found a measurement interval of 30 seconds works best for this workload. The FFT approach initially correctly chooses an interval between 25 and 30 seconds. But after some time, because of the erratic nature of the bandwidth, it drops to between 3 and 10 seconds, causing it to diverge a little bit for the interleave ratio. Despite this, at the end, it still recovers. And the FFT approach still results in performance only 3% slower on average than the best fixed interleave ratio that we found. So now let's look at how DMI handles changes in bandwidth demand. We do this by starting an instance of the LBM workload using 20 cores, and after 300 seconds, starting another instance using remaining 51 cores. The plot above shows the interleave ratio DMI chooses in orange, and the number of CPUs that are being active at a time in blue. So here in the beginning, DMI approaches the interleave ratio with the first instance of LBM running alone. And then after 300 seconds, the second instance of LBM begins, causing DMI to decrease its interleave ratio to handle the increased bandwidth demand. And then at around 650 seconds, the second instance of LBM ends, and DMI returns to its original interleave ratio. Because DMI adjusts to the bandwidth demand of the system, it performs at least 4% faster than any single static interleaving ratio. So in conclusion, effectively utilizing the bandwidth is important for application performance. And static interleaving is insufficient for shifting bandwidth demands. We showed how to dynamically utilize system bandwidth DMI, which is on average 18% faster than colloid for bandwidth-intensive applications, and can also outperform static interleaving when the bandwidth demand is variable. The kernel changes needed for the migrator have also been merged in Linux since version 6.17, allowing this to be more easily used. Thank you. Any questions?
Yeah, interesting talk. So I've not read the paper, so you might have addressed this. So around about maybe 8 years ago, right, there was this whole line of research on DRAM caches, where you have die-stacked DRAM, and then you could add that as a cache level to normal processors. And people then studied this very similar problem, right? So you have this DRAM cache level, and then the memory, and there are these two tiers. And then the question is, how can you actually consider bandwidth to use this die-stacked DRAM cache effectively? So have you looked at that line of research? And so in particular, I'm understood what is actually different in these two contexts?
I don't think I've seen work in related to that context. In the paper I cite similar work in terms of like NUMA machines. And basically what I found that either for those works specifically, either they rely too many on the properties of being a NUMA machine rather than CXL, or they're just not as sophisticated. But for the die-stacked DRAM, I can't specifically answer that question.
We've got time for another question. Would you mind me asking a terribly naive question?
Please.
This is a little outside my area. So I missed something crucial at the beginning.
Sure.
So what I got was that in a place when you're choking the memory bandwidth, you want to, I assume that the goal here is to restrict the use of the memory bandwidth by using interleaving of the or putting some of the hot pages across the CLX so they're not using the memory bandwidth. Is that they're reducing their memory bandwidth pressure?
Yeah, it's reducing the pressure. Let me see if I could find the slide.
Yeah.
So like here with basically all the memory accesses are going to the local node, but it's higher than what it's more requests than what the memory controller can handle. So you have queuing effects, which increase the latency, which limits the bandwidth. If you instead move some of those requests to CXL, now you have maybe about the same amount of bandwidth being served on the local node, but now you have you've added another line for people to queue, and you could serve more requests that way. Does that answer your question?
Yeah, it does. Yeah.
Okay.
But it's slightly counterintuitive that you're putting your hot pages in the remote place. But I totally get it. And that was what tripped me up. Thank you. Yep. We've got time for another question.
Very, very interesting talk. I wonder, is there a possibility that because of those migrations, you end up causing more, you get like a higher bandwidth, but basically you caused like more last level cache misses because you kept migrating stuff.
Like basically, does the cost of migration hurt you more than the bandwidth benefits?
Yes, but actually I now realize that my question made no sense. I'm sorry for that.
Okay. I mean, it's a concern.
No, what you are saying makes sense. My question was different, but.
Oh, okay. Yeah, sorry.
Feel free to ask.
Oh yeah, so yeah, there are costs of migration. We found in this, especially because we had only one thread doing migrations, that one core out of 72, we didn't see a big impact on the workloads that we're running. Maybe if you sped it up where maybe the workloads are much larger, you want more migration threads to get it to where it needs to be quicker, then you might have to consider the trade-off of how many threads are used to migrate versus not. But we didn't, with our one thread, we didn't see that many downsides of migrating.
Just one last comment. I thought the way you used the FFTs was really cool.
Oh, thank you.
Coincidentally, we did something like that in a large-scale service in Google, my colleague and I, and it worked very, very effectively on this very diverse, very large workload. So it's really cool to see you doing something like that.
Oh, thanks.
All right. Any last questions? In that case, let's thank the speaker for a great talk.
Thank you.
I just wanted to thank the audio-visual team for sorting everything out and being brilliant, and all the PLDI organisers and all the speakers, invited speakers. Young Ho and Tom Ahura have done an amazing job of putting together a program committee and program for this. And yeah, general chair for ISM is actually quite an easy job because PLDI do nearly everything. So thank you, everyone.